Let's start out with a little game. So we're going to take a positive integer, or maybe a few positive integers, and write them as addition problems. So what do I mean by that? Well, we're going to expand, for instance, a number n into this sum, lambda 1 plus lambda 2 plus lambda 3 up to lambda k, where there's some ordering on the number lambdas. So lambda 1 is the biggest. It's bigger than or equal to lambda 2, which is bigger than or equal to lambda 3, all the way down, and they're all bigger than or equal to 1. And we're going to do this expansion into an addition problem using two different rules. So the first rule is every number on the right-hand side, that's over here, has to differ by at least 2. So for instance, part of your addition problem could be 9 plus 7, because those two numbers differ by 2. You could also have 13 plus 4. Those differ by 9, but 9 is obviously bigger than 2. But you could not have something like, for instance, 8 plus 7. Those only differ by 1. That's not a big enough difference. And then for the second rule, we're going to only use numbers from the two lists given right here. So our first list is 1, 6, 11, 16, 21, 26, and so on and so forth. That's everything that has a remainder of 1 when divided by 5. And the second list is 4, 9, 14, 19, 24, 29. That's everything that has a remainder of 4 when divided by 9. Okay, so let's play this game for a couple of numbers. So let's start with the number 5. So observe that we could write that as 5. So this only has one piece. So this difference condition right here doesn't really apply. We could also write it as 4 plus 1. So notice the difference between 4 and 1, well, that's 3, which is most definitely at least 2. The next kind of obvious way that we could write 5 is as 3 plus 2, but 3 and 2 only differ by 1, so that doesn't work. And now let's maybe note here something that may not seem important right now, but it will be important, and that is the number of ways we can do this, expansion into an addition problem. And in this case, there are 2 ways of doing that. Now let's move over here and decompose 5 into parts using our second rule. So here we can either write it as 4 plus 1. We're allowed to use 4 here and 1 here, or we could write it as 1 plus 1 plus 1 plus 1 plus 1. Notice there's no difference condition over here in this second rule. And then those are the only ways that we can write 5 as an addition problem using this second rule. And how many ways are there? Well, there are 2 ways again. Okay, let's move on to maybe the next number. And so that would be 6. So observe that we can write that as 6, we can write that as 5 plus 1, and we can write that as 4 plus 2. Again, the next obvious thing would be to write it as 3 plus 3, but those are the same number. They do not differ by at least 2. Now, counting this up, over here using rule 1, we can decompose 6 3 different ways. And now let's see how many ways we can do it using rule 2. So we can decompose it using 6 itself. Notice that's in our first list. We can decompose it as 4 plus 1 plus 1, or 1 plus 1 plus 1 plus 1 plus 1 plus 1. Again, there are 3 ways in this case as well. Okay, well now something fishy is happening. It looks like the number of ways to decompose a number using the first rule may be the same as the number of ways to decompose a number using the second rule. But let's do one more exploratory example before we make that maybe an official guess. So let's do 9. So we can write that just as itself, as 8 plus 1, as 7 plus 2. We can write it as 6 plus 3. Notice we cannot write it as 5 plus 4 because those don't differ by at least 2, but we can write it as 5 plus 3 plus 1. But how many ways can we do this? Well, just adding those up, those are 5 different ways. Now, if we can take the number 9 and expand it 5 different ways using rule 2, then maybe we could have a guess that these two, numbers of ways of expanding numbers are the same. So let's see. So if we have 9, notice we're allowed to use 9 here. So we have 9. Then the next way would be 6 plus, well, kind of 6 plus 3, but we'll write it as 6 plus 1 plus 1 plus 1 because we can't use 3 itself. And then after that would be 4 plus 4 plus 1. And then after that would be 4 plus, well, now it's just going to be a bunch of 1s. So let's see, 1, 2, 3, 4, 5 1s. And then our very last way will be with 9 1s. So I'll just put a bunch of dots there, but I have 9 1s. But observe, how many ways can we expand 9 using the second rule? Well, there are exactly 5 ways again. And, well, in fact, this coincidence is not really a coincidence at all. It holds for every number. So in other words, if you take the number 12,572 and you expand it into addition problems using this first rule, you count up how many ways you can do that. You expand it into addition problems using the second rule, and you count out how many ways you can do that. Well, those two numbers will be the same. And that's in fact what we're going to prove inside of this video, but we're going to need a lot of background information to get to it. So let's maybe start by looking at this game that we have up here, but in a more careful way, and that is with the study of so-called integer partitions. So let's look at the precise definition of a partition. So given a non-negative integer n, a partition of n is a tuple. I'll call that tuple lambda. And here I've written it as a k-tuple. So it has entries lambda 1, lambda 2, all the way up to lambda k. And it's got to satisfy 2 conditions in order to be a partition. First of all, lambda 1 is bigger than or equal to lambda 2, which is bigger than or equal to lambda 3, all the way up, which is bigger than or equal to lambda k, which is bigger than or equal to 1. So there's some sort of ordering here. And then next up, I guess the most important part is that the sum of the lambdas equals our number n. That's why it's a partition of n. So like I said, lambda 1 plus lambda 2 all the way up to lambda k is n. And this number k, which I have up here, is, well, that's the number of parts of the partition. Or we might say that lambda has k parts. Okay, so let's look at some really, really simple examples. So let's start with the quadruple 3, 2, 1, 1. And let's notice that this is a partition of what number? Well, it's going to be of 7 because 7 is equal to 3 plus 2 plus 1 plus 1. Furthermore, we say that this partition has 4 parts. Well, I think that's kind of obvious because it's a quadruple. It has 4 entries there. And then, maybe for one more, we have 5, 4, 2, 2, 1. And so this is a partition of, I think it's going to be 14. And well, that's because we have 14 is equal to 5 plus 4 plus 2 plus 2 plus 1. And furthermore, this is with 5 parts. And now, maybe before we move on, let's just briefly note the following. Instead of writing the tuple, we often just write the addition problem. So in other words, we would say that 3 plus 2 plus 1 plus 1 is a partition, instead of writing it like the tuple. And then I guess maybe the first big question that one might ask is, given n, and so here we're taking n to be a non-negative integer, how many partitions of n are there? Okay, so let's start to explore that question. Now, in order to explore that, we're going to introduce the notation P of n. So this is called the partition function. And so P of n is simply the number of partitions of our non-negative integer n. So let's by hand calculate a couple of the first values of P, starting with n equals 0. Now, you might say, well, there should be 0 partitions of 0, but in fact, we take P of 0 to be equal to 1. And we think about this as the empty partition. You know, like there is a single set with 0 elements, the empty set. Well, there is a single partition of the number 0. It is called the empty partition. And maybe as a tuple, it would look like that. So, well, there's nothing in there. Okay, so now let's move on to n equals 1. And so, well, this is pretty straightforward. Notice that P of 1 is equal to 1 because, well, we simply just have 1 itself. Now, moving on, so n equals 2, you know, we can pretty quickly see that P of 2 is equal to 2. And that's because, well, we have 2 and we have 1 plus 1. Those are our two partitions of 2. Now, let's move on. N equals 3. Let's see if we can count those up. So we'll have 3. And then next up, we'll have 2 plus 1. And then next up, we'll have 1 plus 1 plus 1. So that means that P of 3 is equal to 3. So immediately it looks like P of n might be equal to n, but as we see, that's going to stop working immediately at n equals 4. So let's write down the partitions of 4. Well, we have 4, we have 3 plus 1, we'll have 2 plus 2, and then maybe next we'll have 2 plus 1 plus 1, and then finally 1 plus 1 plus 1 plus 1. But if we count that up, 1, 2, 3, 4, 5, we see that P of 4 is equal to 5. And then, well, maybe I'll leave as a little exercise for n equals 5. You can write these down pretty easily, and you'll see that P of 5 is equal to 7. So there's, in fact, 7 partitions of 5. And then, well, I'd just like to quickly point out that this number gets large very, very quickly. So in fact, if you count up the number of partitions of 10, you get 42. If you count up the number of partitions of 50, so I kind of dare you to try to write all those down, there's going to be 204,226. If you count up the number of partitions of 100, how many are you going to get? Well, you're going to get 190,569,292. And so in the grand scheme of things, 100 isn't so big, but notice there are a ton of partitions of 100. And then maybe if we were to go one order of magnitude higher, the number of partitions of 1,000, well, that's going to be on the order of 2 times 10 to the 31. So as you can see, this is growing quite quickly. So there are a number of approximations to the partition function. Maybe one of the most famous was by Ramanujan. So let's move on to looking at that. It's really hard to pin down a formula for the number of partitions of an integer n. So an early formula that looked at this was from 1918, and it's due to Hardy and Ramanujan. And it gives you an asymptotic behavior of this partition function P of n. And what this is saying is that this grows similar to the function 1 over 4 times n times the square root of 3 times e to the pi times the square root of 2n over 3. So as you can see, this is a really complicated asymptotic formula. But if you look at the graph of these next to each other, where the dots are the partition function and the line is that asymptotic formula, you can see that it does pretty well approximate the value of the partition function. And that's just for all the numbers up to 20. And so notice that the number of partitions of 20 is getting pretty large pretty quickly. Notice that it's over 600. And then as we move forward, you can see that the partition function and this asymptotic approximation are pretty well fit. Notice that when we're around 1,000 for n, the number of partitions of n is really quite large, in the order of 10 to the 31. And notice that as we get to 10,000 for n, the order of the number of partitions is 10 to the 106. So that's bigger than a Google. Now in 1937, Hans Rademacher came up with this formula for P of n that was an infinite sum. So notice that this infinite sum is super crazy. It involves lots of pieces that just seem to be coming out of nowhere. Recall that the left-hand side of this, P of n, is always a positive integer. So I think it's pretty interesting even that this right-hand side produces a positive integer ever, needless to say, all of the times. So notice there are tons of irrational parts in here. We've got square roots of 2/3 times this n minus 1 over 24. We've got a square root of 2. We've got pi. We've got lots of parts that are pointing towards irrationality, but somehow we get a positive integer for every value of n here. Now notice that there's this value a sub k of n, and I'm not going to talk so much about this number a sub k of n. I'll just say that it's a pretty complicated object. But since this sum is complicated on its own, the fact that we have to talk about this one part as being another complicated object really just points towards how complex this formula for P of n is. And I guess we should say that this is an infinite sum formula for P of n, which would be a little bit nicer to have some sort of finite version of a formula for P of n. And these four mathematicians in 2011, Brunier, Folsom, Kent, and Ono, in fact came up with this finite formula for the partition function P of n. But it involves some very, very modern mathematical objects. That being said, it is a finite sum, which makes it a little bit nicer from a philosophical point of view to the infinite sum that we saw before. And I'll just say that these Q of n, A of Q, and P are very complicated modern objects. And if you want to look into this more, here are some keywords. You want to look for this thing called the modular group, weak Moss forms, and etc. So this comes from a part of number theory known as the study of modular forms and some sort of weakening of the notion of a modular form. Okay, so now that we've seen how complicated integer partition formulas are, what are some interesting questions or results involving these integer partitions? Well, we're going to look at two main types of results. One involves congruences, so we'll just call them Ramanujan type congruences. And then one of them will be identities involving restricted partitions. So maybe the most famous Ramanujan type congruence is that P of 5k plus 4 is congruent to 0 mod 5. So that means anytime you've got a number that's of the form 5k plus 4, for instance, 4, 9, 14, 19, 24, so on and so forth, the number of partitions of that number is a multiple of 5. So that's how we read that. And here you can see this worked out explicitly. So the number of partitions of 4 is 5. That's 5 times 1. The number of partitions of 9 is 30. That's 5 times 6. All the way up to what we've got here is the biggest, the number of partitions of 29 is 5 times 913. Now there are some other classic Ramanujan type congruences due to Ramanujan. And well, I guess maybe the next two most well known are P of 7k plus 5 is congruent to 0 mod 7, and P of 11k plus 6 is congruent to 0 mod 11. But in fact, there are lots of these congruences. In fact, as we'll see, there are an infinite family of such congruences. And so perhaps the next batch were discovered in 1960 by Aitken. And these are of the form P of 11 cubed times 13k plus 237 is congruent to 0 mod 13. So this is obviously much more complicated than what we saw from the original congruences, but this is still a result in that spirit. And there are even more, like this one due to Ono. So notice that the number of partitions of numbers of the form 107 to the 4 times 31k plus 300645597 is congruent to 0 mod 31. And this is where we get a result that is actually part of an infinite family of congruences. And in 2001, Weaver, in fact, found an algorithm for producing these types of congruences, and with this algorithm constructed 76,065 examples of Ramanujan type congruences. And then in 2012, there was an extension to Weaver's algorithm that produced another, 22 billion examples of Ramanujan type congruences. So here's a particularly crazy one. So this is numbers of the form 999959 to the 4th power times 29k plus, well, I won't read that number off. So numbers of that form, the number of partitions of numbers of that form is congruent to 0 mod 29. The other family of so-called interesting results that we'd like to look at involving integer partitions are what we'll call restricted partition identities. So let's say you've got p sub 1 of n, which is the number of partitions satisfying what we'll just call rule 1. I think this will be clearer once we look at what these rules actually are. And then p sub 2 of n is the number of partitions satisfying rule 2. So what we'd like to do is find these two different rules so that p1 of n and p2 of n are the same. So a very early example of a restricted partition identity is from Euler in 1748, and it was shown, or he showed, that the number of partitions of n with distinct parts is equal to the number of partitions of n with odd parts. So we can see an example of this identity working if we look at all the partitions of 6. So the partitions of 6 with distinct parts are 6, 5 plus 1, 4 plus 2, and 3 plus 2 plus 1. There are 4 such partitions. And then the partitions of n using only odd parts is 5 plus 1, 3 plus 3, 3 plus 1 plus 1 plus 1, and then we've got 6 ones. But notice that there are 4 integer partitions of that type as well. Now we could look a little bigger, so the number of partitions of 10 with distinct parts, so we've got 10, 9 plus 1, so on and so forth, down to this last one, 4 plus 3 plus 2 plus 1. And then you can also look at the number of partitions of n using only odd numbers, so 9 plus 1, 7 plus 3, all the way down to just a string of 10 ones. And if you were to count these up, these numbers are the same. So let's see, there are 10 of each type of these partitions. And now here's where we want to reword these rules a little bit so that they can be generalized. So let's look at the number of partitions of n with distinct parts and observe that we could rewrite that condition as the number of partitions of n whose parts differ by at least 1. And notice implicitly here we have the number of partitions whose adjacent parts differ by at least 1, but we don't actually need that word adjacent because we've got our ordering of the partitions from greatest to least. And then the number of partitions of n with odd parts can be rewritten as the number of partitions of n whose parts are congruent to either 1 mod 4 or 3 mod 4. But we could just write that as plus 1 minus 1 mod 4. And so you can think that all of the odd numbers, when you divide them by 4, either have a remainder of 1 or a remainder of 3. So this does capture all of the odd numbers. And now the question is, can we change this number 1 in the parts that differ by at least 1 and pick up a change to this number 4 in the congruent to plus minus 1 mod 4? And then perhaps we would have some sort of family of identities like this. And in fact, yes, we can. And changing the 1 to a 2 and the 4 to a 5 gives us the first Rogers-Ramanujan identity. And so we could just read this off. So the number of partitions of n whose parts, remember that really means adjacent parts, differ by at least 2, is equal to the number of partitions of n whose parts are congruent to plus minus 1 mod 5. Notice that's equivalent to parts that are either 1 mod 5 or 4 mod 5. And now the proof that we'll present for this identity will use the machinery of generating functions. So let's get started by looking at the basics of generating functions. Generating functions happen to be one of my favorite tools for solving certain combinatorial problems. But what is a generating function? So let's look at the definition. Given a sequence of numbers, so I'll call those numbers a sub n, indexed for n between 0 and infinity, the generating function for this sequence, well, it's simply a power series where the coefficients of whatever variable you're using are the entries from the sequence. So in other words, a of q is equal to the sum as n goes from 0 to infinity of a sub n times q to the n. Here are the first couple of terms. And so in this setting, since we're working with, or our main goal is to look at partition type identities, we're using q as our formal variable because that's standard in this setting. So the simplest example would be, well, what happens if you have a constant sequence? For instance, if the sequence is just, well, 1. So in other words, if you list out the elements, it's 1, 1, 1, 1, so on and so forth. Well, in this case, you're just simply summing powers of q, but then by the geometric series summation rules, that sums to 1 over 1 minus q. And to put this into terms that we've been talking about, observe that there is exactly one way to write n as a sum of numbers just using 1. In other words, there's only one partition of n where all of your parts equal to 1. And of course, that's the partition 1 plus 1 plus 1, and so on and so forth. And so this is in fact the generating function for that type of partition. Anyway, let's look at a maybe more interesting example. So we have this nice recursively defined sequence, and often recursively defined sequences are well suited to using generating functions. So we have the 0th term is equal to 1, and then the nth term is equal to 2 times the n minus first term plus 3. Okay, so let's see if we can use this data to get a closed form using generating functions. So let's start with a of q, which we're defining to be the sum as n goes from 0 to infinity of a sub n times q to the n. Now observe that our recursion doesn't take over until n is bigger than or equal to 1. So what we need to do is split off the 0th term. But observe that the 0th term is 1, so that's simply going to be a 1. We have 1 plus the sum as n goes from 1 to infinity of a sub n times q to the n. Okay, but now we're going to observe that this a sub n term here can be rewritten using the recursion that's defining our sequence, given that the index here is, well, at least 1. So let's make that rewriting step. So now we have 1 plus, we've got our sum as n goes from 1 to infinity, but now we have 2 a n minus 1 plus 3 times q to the n. And now let's maybe underline this in green. That is the substitution that we made. Now let's split this into pieces. So we're going to have a 1 plus the sum as n goes from 1 to infinity of a sub n minus 1 times q to the n. I'm going to factor that 2 out. And then we're going to have plus the sum as n goes from 1 to infinity of 3 times q to the n. Okay, but now let's re-index maybe this first sum. So I can take this first sum and replace every n with an n plus 1. And that's going to change this lower bound of my sum. Instead of starting at 1, it starts at 0. And then here I'm going to have, instead of this being n minus 1, I'll have an n, and then here we'll have an n plus 1. Now what I'll do is I'll take this n plus 1 and I'll factor a q out, making it q times q to the n. I'll take the q outside of the sum. So now I'll have 1 plus 2 times q times our sum as n goes from, now it's 0 to infinity, of a sub n q to the n. And then, well, luckily, look at this. That's exactly a geometric series. Now, instead of like over here where the starting term was 1, Now the starting term is 3 times q, but the common ratio is still q. So this sums to 3 times q over 1 minus q. And then also, let's look closely at this sum that's left over and observe that that is our original generating function, a of q. So look, we started over here at a of q, and we ended up with an expression over here that involved a of q. So that gives us some motivation to solve for a of q. We essentially have an algebraic equation for a of q. So moving that over, we'll have 1 minus 2 times q times a of q. Notice that's connected to a 2 times q. And then maybe for the sake of simplification, let's take this number 1 and we'll write it as 1 minus q over 1 minus q, just to combine with this 3q over 1 minus q. So here we're going to have this is equal to 1 plus 2 times q over 1 minus q. But now let's see, that means that our a of q is equal to 1 plus 2 times q over 1 minus 2 times q times 1 minus q. Okay, nice. But now what we can do from here is use the standard trick of partial fraction decomposition and split this into 4 over 1 minus 2 times q minus 3 over 1 minus q. And then after that, we can re-expand that as 2 different geometric series, and we'll end up with the following formula. So I'll push them back together. So we'll have the sum as n goes from 0 to infinity of, so that's going to be 4 times 2 to the n minus 3 times q to the n. But now let's connect the dots. Observe up here, we said that a of q is equal to an times q to the n, but down here we discovered it's equal to 4 times 2 to the n minus 3 times q to the n. So that means by equating coefficients, we have a sub n equals 4 times 2 to the n minus 3. Okay, good. So now that we've got this idea of how generating functions look, let's see how it can be applied to the partition function. Now that we've seen something about generating functions, we'd like to look at the generating function for the number of partitions of n. And so I want to make this claim, and this is kind of a hand-wavy argument, that the generating function p of q, and so this is the generating function, like I said, for the number of partitions of n, is the following infinite product. So we have 1 over 1 minus q times 1 over 1 minus q squared times 1 over 1 minus q cubed, and so on and so forth. Where, of course, we interpret each of these as being expanded as geometric series. And so just in a few minutes, we're going to look at a careful proof of this after we build up a couple of more tools. But I think it's nice right now to take a step out and look at the idea of why this works. So let's take this infinite product, this 1 over 1 minus q times 1 over 1 minus q squared, and so on and so forth, and let's expand each of the parts as geometric series. So if we expand the 1 over 1 minus q, we clearly get 1 plus q squared plus q cubed, so on and so forth. But what I'd like to do is take the q squared and write it as q to the 1 plus 1, q cubed and write it as q to the 1 plus 1 plus 1, and then so on and so forth. So here, that's all coming from the 1 over 1 minus q. And then we'll do something similar for the 1 over q 1 minus q squared term. So we'll expand that as a geometric series, but we'll write those exponents as q to the 2, q to the 2 plus 2, and so on and so forth. And then we'll continue doing this. So in general, if we have 1 over 1 minus q to the k, we would write those exponents as q to the k plus k, and so on and so forth. So now what I'd like to do is see what happens as we multiply out these infinitely many terms and keep track of all of the different ways we can achieve certain powers of q. So let's observe that if we simply take 1 from each of the terms and multiply all those together, that gives us the number 1. And that falls in line with the fact that we take the number of partitions of 0 to be equal to 1. It's like the empty partition. Then we can look at all of the ways to achieve q to the first power, but in fact, there's only one way to achieve q to the first power. And that's taking q to the first power from the first term, and then 1 from all of the remaining terms in the product. But now it gets a bit more interesting when you look at the q squared terms. We could look at q to the 1 plus 1 times 1 times 1, so on and so forth. But we could also look at 1 times q squared times 1 times 1, and so on and so forth. That's also going to give us a q squared. Now, obviously, we can put these two together to give us 2q squared. And notice that 2 is the number of partitions of 2. Now, we can keep doing this, like, for instance, with q to the 1 plus 1 plus 1 times a bunch of 1s. So in the product there, that will give us a q to the 1 plus 1 plus 1 term. Or we could have, let's see, q to the 1 times q squared times the rest 1s. And so that gives us a term that looks like q to the 2 plus 1. Or we could have a 1 times q cubed times all 1s, and that's going to give us our q cubed term. Now, of course, we could add all those together because they're like terms, and that's going to give us 3 times q cubed. So notice that we're encoding the partitions of n in the exponents of q, and that's going to naturally give us the correct coefficient. And this is something that's going to extend on and on and on. Okay, so that's the idea for why this partition function takes this form. Now I'd like to look at a little bit more careful proof, but before we do that, we need to look at a couple of more tools. So the first result that we'll need is a bit of a technical result that builds a recursion among certain types of partitions of n. So let's consider this function p of nk, and this gives us the number of partitions of n whose parts are less than or equal to k. So for example, if we take n to be equal to 8 and k equal 3, we're looking at the number of partitions of 8 whose parts are less than or equal to 3. Now I'd like to observe that we can take these partitions and sort them as follows. So notice that we can sort them into the partitions where 0 parts are equal to 3, 1 part is equal to 3, or 2 parts are equal to 3. Notice that if you've got 3 or more parts equal to 3, then you're a partition which is bigger than or equal to 9, so that's strictly bigger than 8. So that's why we don't have anything above that. So now looking at this a little bit closer, notice that the partitions with 0 parts equal to 3 are simply partitions of 8 whose parts are less than or equal to 2. And then the partitions where 1 part is equal to 3, that gives us really partitions of 5, because 5 is 8 minus 3. We're taking away that 1 part which is equal to 3. So partitions of 5 whose parts are less than or equal to 2. And then finally, if we have 2 parts equal to 3, we're really looking at partitions of 2. That's 8 minus 2 times 3. So partitions of 2 whose parts are less than or equal to 2. Now that gives us this, like I said, nice recursion. So we've got p of 8, 3 is equal to p of 8, 2 plus p of 5, 2 plus p of 2, 2. Now, of course, we'd like to have something a little bit more general in this. So if we take the general case, so p of nk, here we're looking at partitions of n with parts less than or equal to k. We can split this into pieces. So we could have 0 parts equal to k. And so maybe we take a partition that has that rule. So 0 parts are equal to k. We'd say it's lambda 1 plus lambda 2 all the way up to lambda m. Well, so notice if 0 parts are equal to k, then that means that this is really just a partition of n whose parts are less than or equal to k minus 1. And then how many partitions are of this form? Well, there's p of n k minus 1. And now if we look at the partitions where 1 part is equal to k, so this would look like k plus lambda k, or sorry, lambda 2 plus lambda 3 all the way up to lambda m. And then the tail of this is simply a partition of n minus k whose parts are less than or equal to k minus 1. And we can easily count up the number of partitions of this form as well. There are p of n minus k, comma k minus 1. Now we can keep going. So just to do one more explicitly, if you have two parts equal to k, so that would be k plus lambda 3 all the way up to lambda m. Now the tail of this will be a partition of n minus 2k whose parts are less than or equal to k minus 1. And the number of partitions of this form is kind of clearly equal to p of n minus 2k, comma k minus 1. Now we could keep going here, but I think it's becoming a little bit clear that we have the following formula. So this is like a nice recursion. I think this is a nice recursion at least for p of nk. So we've got p of nk is equal to p of n comma k minus 1 plus p of n minus k comma k minus 1 plus p of n minus 2k comma k minus 1, and so on and so forth. And that's going to stop when you have n minus something times k is less than 0. Now we could put this all together as p of nk is equal to the sum as j goes from 0 to infinity of p of n minus jk comma k minus 1. And you might say, well, this is an infinite sum, but in fact it's not really an infinite sum because this will truncate. Whenever jk is strictly bigger than n, well, the number of partitions of a negative number is obviously going to be 0 because we're only using positive parts in our partition. And so this is the recursion that we'll use, or this is a recursion that we'll use as we do our careful proof for the generating function for the number of partitions of n. That being said, we need one more little result before we look at that careful proof. And that result is that the number of partitions of n whose largest part is k is equal to the number of partitions of n with k parts. Now, this is kind of equivalently equal to the number of partitions of n with parts less than or equal to k is equal to the number of partitions of n into k or fewer parts. So let's look at a quick example of this. So a partition of 19 whose largest part is 7 would be 7 plus 5 plus 3 plus 2 plus 2. That's an example of a partition of 19 with this rule. Now, I'm introducing something called a Farrer's diagram here. We're not going to look at these super in-depth, but this is just a diagram with a number of dots corresponding to the size of each partition, or part of the partition. So we've got 7 of those purple dots, that's for our 7, 5 of the red dots, that's for our 5, so on and so forth. Now, I'd like to copy this over here and observe that if we do a little reflection about a diagonal, that's going to turn into a new partition. And that's a partition with 7 parts. And notice here we have 19 is equal to 5 plus 5 plus 3 plus 2 plus 2 plus 1 plus 1. And so this reflection about the diagonal, this is called finding a conjugate partition, is in fact a bijection that takes a partition whose largest part is 7 into a partition with exactly 7 parts. We can see this a little bit more generally as follows. So let's say we've got a partition of n whose largest part is k. And so that means it has k dots on the top and then, well, you know, kind of whatever after that. And now we can reflect that about that diagonal, and that's going to give us a partition with k parts. And this is a one-to-one and onto. In other words, it's an invertible transformation. And so since it's an invertible transformation, that's how we get this equivalence of the number of partitions with each of these rules. Okay, so those were our 2 preparatory results before we look at the careful proof for the closed form of the generating function for the number of partitions of n. Now let's look at a careful proof that the generating function for the number of partitions of n, which we'll call capital P of q, is in fact equal to, well, this product that we alluded to. And the way that we'll do this is to look at a finite version of this. So let's write p sub k of q equal to the sum as n goes from 0 to infinity of Pn comma k times q to the n, where that Pnk is the number of partitions of n with parts less than or equal to k, which we already talked about. And so what we'll do is show that this p sub capital N of q is equal to the product as m goes from 1 to n of 1 over 1 minus q to the m. But then if we take the limit of this as capital N goes to infinity, well, this left-hand side coincides with the left-hand side up here, and then the right-hand side coincides with the right-hand side up here, thus proving, well, that this generating function has the form that we want it to have. Okay, so we'll prove this statement down here by induction. So let's start with our base case, which will be the case when capital N is equal to 1. And this is pretty quick. So we're going to take p sub 1 of q, but then by definition, that's going to be the sum as little n goes from 1 to infinity of p sub little n comma 1 q to the n. But then, well, let's extract part of this and look at really what we're looking at here. So this p sub n comma 1, that's the number of partitions of the number n with parts, well, parts less than or equal to 1. But since you can't have less than 1, it's going to be parts equal to 1. But now let's observe that that's pretty clearly equal to the number 1 all of the time. And that's because our only partition here is the partition, which I'll say n is equal to 1 plus 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 1, and so on and so forth. N copies of 1. There's no other way to build a partition of n using only 1. So that means this turns into this sum as n goes from 0 to infinity of q to the n, but that's a well-known geometric series. And as a well-known geometric series, we know that it has a closed form as a rational function of 1 over 1 minus q. Okay, so that sorts out the base case. And now let's move on to our induction step. So for our induction step, we clearly need to make an induction hypothesis. So let's suppose for some k bigger than or equal to 1, we have the following. P sub k of q is equal to this product as m goes from 1 to k of 1 over 1 minus q to the m. In other words, it has the correct format. And then, well, we want to consider the next case. So let's do that. We're going to consider p sub k plus 1 of q. And so that's going to be equal to, by definition, the sum as n goes from 0 to infinity of p of n comma k plus 1 q to the n. But then, as we just explored, we know that we can decompose this p of n comma k plus 1 into a bunch of pieces. And so first of all, we can decompose it into p of n comma k. So this will be if we use the part equal to k plus 1 0 times. So I'll write that here. So we use k plus 1 0 times. Okay. And then after that, we'll add this to p of n minus k plus 1 comma k. And well, this is where we use k plus 1 one time. So if we use k plus 1 one time, then we're left over with the number n minus k plus 1. But if we're only using k plus 1 one time, then that means we have to use k or less after that. That's why we get this n minus k plus 1 comma k. Well, and this is just going to continue on and on and on. So then we're going to have plus p of n minus 2 times k plus 1 comma k. And well, this is going to be from using k plus 1 2 times. Because if we use it twice, then the number left over will be n minus 2 times k plus 1. And we're only allowed to use k or less to decompose that. And then, well, that's going to continue on and on and on. And this actually turns into an infinite sum. And, well, it may not seem like it should turn into an infinite sum. Well, it only turns into an infinite sum because after some point, all of those numbers are equal to 0. And it'll be advantageous for us to write it as an infinite sum. Okay, so let's do that. So we're going to write this as the sum as n goes from 0 up to infinity. And then inside of this sum, I'm going to write this as the sum as j goes from 0 to infinity of p sub n minus j times k plus 1 comma k. And then all of this whole sum is multiplied by q to the n. So observe that what's happening in this yellow circle is all being put into this inner sum. Okay, great. And now, well, we're going to do something that we do quite often in this sort of calculation, and that is re-index. So I'm going to re-index this sum by replacing all of the n's with n plus j times k plus 1. And you might say, oh, well, that's going to be a bit tricky because that's going to change my starting point for n to something like negative j times k plus 1. But in fact, all of those negative numbers will simply give us 0 because we don't talk about partitions of negative numbers. So that means our lower bound stays at n equals 0. So now what are we going to have here? Okay, so now we're going to have this sum as n goes from 0 to infinity. And then inside of that, we're going to have this sum as j goes from 0 to infinity. Now it's going to be p of n comma k because of our re-indexing. And then it'll be q to the n plus j times k plus 1. So let's write that, n times j times k plus 1. Okay, so I think that's looking pretty good. But now I'm going to pull this into some pieces. So I'm going to take this n plus j times k plus 1 and pull it apart into q to the n, and then q to the j times k plus 1. So let's do that. So that's going to leave us something like this. And then furthermore, I'm going to change the order of summation. Remember, everything here is happening formally, so we don't have to worry about convergence. So now outside, we're going to have the sum as j goes from 0 up to infinity. And then we'll have our sum as n goes from 0 up to infinity of p of n comma k times q to the n. And then after that, we're going to have q to the k plus 1 raised to the j power. I'm careful to write it like that. Okay, but now observe what we have here is the induction hypothesis built in to this equation. So let's underline that. So here's our induction hypothesis that p sub k of q is equal to this product. But observe that p sub k of q is also equal to this sum, just, by definition. So these two are equal. So in the next step, I'm going to replace, well, that thing that I have overlined in blue by the appropriate product. Furthermore, that appropriate product doesn't depend on the index j, so I can in fact factor it out. So let's see where that'll leave us. So we're going to factor this out, and we'll have this product as m goes from 0 up to k of 1 over 1 minus q to the m. And then, well, what do we have left over? Now we're going to have the sum as j goes from 0 up to infinity of q to the k plus 1 raised to the j power. But now we've almost got it. Observe this thing right here is another geometric series. The starting term is 1, and the common ratio is q to the k plus 1. So now I can rewrite this as our product as m goes from 0 up to k of 1 over 1 minus q to the m times the rational function version of this geometric series, which is 1 over 1 minus q to the k plus 1. But observe, what I can do from here is just get rid of that 1 over 1 minus q to the k plus 1 and change this upper bound of our product from k to k plus 1. So let's do that. So like I said, we're going to get rid of this, and then we're going to change this k to k plus 1. So we didn't really get into it. We just absorbed it into the notation of that product. Okay, so there we have it. Now we have our careful proof that p sub n of q is equal to the product as m goes from 1 to capital N of 1 over 1 minus q to the m. And like I said, from here all we have to do is take the limit of both sides, giving us this classic formula for the generating function of the number of partitions of n. Okay, so now that we've proved a nice closed form for the generating function for the number of partitions of n, as this product as m goes from 1 to infinity of 1 over 1 minus q to the m, let's see what we can do if we have restricted partitions. So let's say that p sub restricted of n is the number of partitions of n with a certain restriction. So of course we can just write down the generating function for that. So we've got p res q is the sum as n goes from 0 to infinity of p res n q to the n. That's just using the definition of a generating function for a certain sequence. But what we'd really like is to have this as some sort of product of rational functions, some sort of nicer closed form. So let's see what we can do to use the normal generating function for unrestricted partitions, maybe decode what parts of this generating function correspond to certain types of partitions, and maybe build nice generating functions for restricted partitions. Okay, so here we've got written out the partition function or the generating function for unrestricted partitions. So I've taken that product and I've just written out the first 5 terms. And I'd like to point out that this 1 over 1 minus q term, as we kind of saw before in the sketch of the proof of this closed form, this corresponds to parts equal to 1. Then, well, this 1 over 1 minus q squared term, like we saw before, corresponds to parts equal to 2, and then so on and so forth. So we've got this 1 over 1 minus q cubed, that's parts equal to 3. This 1 over 1 minus q to the 4th is the parts equal to 4. And then finally, this 1 over 1 minus q to the 5th is parts equal to 5. And so, well, this is an infinite product, so this allows for any types of parts in our partition. Now, the first thing that we can do to make a maybe simple restricted partition generating function is to look at partitions of n using only odd parts. And here, it's really easy to build this generating function. You just simply take the portions of this product that correspond to the even parts and you set them equal to 1. That means that you're only using 0 parts equal to 2, 0 parts equal to 4, 0 parts equal to 6, and so on and so forth. But you're still allowed to use any number of parts that you'd like that are equal to 1, 3, or 5. And so now we could put this all together and we've got p sub odd of q, so that's the generating function of partitions of n using only odd parts. So it's this product right here. We've got 1 over 1 minus q times 1 over 1 minus q cubed, and so on and so forth. So generally, we've got this 1 over 1 minus q to an odd power. We can put this all together into a nice package. So it's the product as m goes from 0 to infinity of 1 over 1 minus q to the 2m plus 1. And now this idea generalizes pretty easily. So let's say we wanted partitions of n using parts not divisible by 3. So we would simply take our big product for unrestricted partitions and we would leave out the parts that correspond to parts that are divisible by 3. So observe here, we've got this big product, but I'm missing the 1 over 1 minus q cubed term, and so that's because our partitions are missing parts equal to 3. And notice that I'm also missing the 1 over 1 minus q to the 6th term, and that's because our partitions with this restriction are missing parts equal to 6. Now, we can also pretty easily package this into a nice product. So we've got the p of things not divisible by 3, or partitions using parts not divisible by 3. So this product is m goes from 0 to infinity of 1 over 1 minus q to the 3m plus 1 times 1 minus q to the 3m plus 2. So that's going to capture all of the numbers that are not divisible by 3. And if you recall, one of the parts of our Rogers-Ramanujan identities involving partitions of n using only parts that are congruent to 1 or 4 mod 5. But using a really similar trick or strategy as to what we just went over for odd parts or parts not divisible by 3, we can write this immediately as a product. So we've got this product as m goes from 0 to infinity of 1 over 1 minus q to the 5m plus 1 times 1 minus q to the 5m plus 4. So obviously the 1 minus q to the 5m plus 1 is corresponding to parts that are equal to 5m plus 1, where m is some non-negative integer, so that's parts congruent to 1 mod 4. And likewise, the other term corresponds to parts of the form 5m plus 4. In other words, parts that are congruent to 4 mod 5. But now let's go and look back at our unrestricted generating function. And what I'd like to do now is talk about some fine control over how many parts of a certain type we have in a certain restriction. So the way to look at this is to take our unrestricted generating function with the big product and expand all of the parts out as geometric series. So this is pretty similar to something that we saw before when we were looking over the intuition for the proof. So this is what I've done here. And as you can see, if we decode this, the number 1 in the expansion of 1 over 1 minus q corresponds to 0 parts equal to 1. This q to the first power, when multiplied out, will be related to 1 part equal to 1 in the corresponding partitions. This q to the 1 plus 1 corresponds to 2 parts equal to 1, and then this just keeps going on and on and on. So q to the 1 plus 1 plus 1 corresponds to 3 parts equal to 1. And then we've got all of these pieces here corresponding to 0, 1, 2, or 3 parts equal to 2. And all of these parts right here corresponding to 0, 1, 2, or 3 parts equal to 3. But notice that these are all infinite sums. So in the unrestricted partitions, we're allowed to use as many parts that we'd like of each type. So that's why we've got this infinite product of infinite sums. Now we can pretty easily start adding restrictions as follows. So let's first look at partitions of n using only distinct parts. And so that means we would leave off the possibility to have 2 parts equal to 1, 3 parts equal to 1, and so on and so forth. But we'd also like to leave off the possibility of 2 parts equal to 2, 3 parts equal to 2, really more than 1 part equal to anything. And that's what we've got going on here. So this first term in the product corresponds to parts that are equal to 1. We're allowed to use 0 or 1 part equal to 1. This second part corresponds to parts equal to 2. We're allowed to use 0 or 1 part. So notice if it's distinct, you can still use 0 parts, but you can use at most 1 part equal to, well, whatever you're working with. So here we've got 0 parts equal to 3, 1 part equal to 3, and finally 0 parts equal to 4, 1 part equal to 4. But still, there's no limit on the size of parts we can use. So this is an infinite product. Now we could package this all together into an infinite product, and this would be maybe p distinct. And this is the product as m goes from 1 to infinity of 1 plus q to the m. And now we can extend this pretty easily. So let's say we were interested in looking at partitions of n using parts at most twice. So I've just called this p sub twice of q. And here we've got this product as m goes from 1 to infinity of 1 plus q to the m plus q to the 2m. We want to think of that 2m as m plus m. That's using m twice. Notice that there's no q to the 3m, which would correspond to using m 3 times. And there's no term q to the 4m or anything higher than that. So if we were to decode this piece by piece, this 1 is 0 parts equal to m. This q to the m is 1 part equal to m. And then finally, this q to the 2m is 2 parts equal to m. And now that we're armed with these strategies, we can pretty easily write down a generating function for a crazy restriction. So just let's build this one. So let's say we want to look at the partitions of n using parts that are congruent to 1 mod 3 at most twice, parts congruent to 2 mod 3 with no restrictions, and then distinct parts divisible by 3. In other words, parts that are congruent to 0 mod 3 at most once. And so as you can see here, we've got 1 plus q to the 1 plus 1. So that would be using the number 1 at most twice. Similarly, we've got 1 plus q to the 4 plus q to the 4 plus 4. So that would be using 4 at most twice. Notice that 4 is congruent to 1 mod 3. And then so on and so forth. Looking more closely at the first part of the product, we've got this first chunk corresponds to parts equal to 1. Like I said before, we can have 0, 1, or 2 parts equal to 1 based off of our restriction. And then this third part in our product corresponds to 0 parts or 1 part equal to 3. That corresponds to having distinct parts equal to 3. 3 is obviously divisible by 3. That's why we have that restriction there. And then this 1 over 1 minus q squared, and likewise on the last slide, the 1 over 1 minus q to the 5th can be expanded as a geometric series, and that's because here we can use as many parts equal to 2, or generally as many parts congruent to 2 mod 3 as we'd like. So anytime you see this 1 over 1 minus something, you really want to think that that is expanded as a geometric series, and that corresponds to using that type of part as many times as you want. Now, we could package this together into one nice product, and I've called this P strange of Q. And here we've got this nice product as m goes from 0 to infinity. We've got 1 plus q to the 3m plus 1 plus q to the 6m plus 2. Notice that is 3m plus 1 times 2. And so that would correspond to using parts of the form 3m plus 1, either 0, 1, or 2 times. And then we've got 1 plus q to 3m plus 3, that's in the numerator as well. So that's using parts of the form 3m plus 3 1 time or 0 times. And then in the denominator, we've got this 1 minus q to the 3m plus 2. And then that is expanded out as a geometric series, and that means we can use parts that are of the form 3m plus 2 as many times as possible. Okay, so now that we've seen this strategy of writing down generating functions for restricted partitions, let's explore some identities involving restricted partitions that arise naturally from manipulating these products of rational functions. Now we're going to look at a way of proving partition identities by manipulating the generating functions. So we're going to start with a really classic result, maybe one that a lot of people know that aren't familiar with a lot of other things involving integer partitions. And we've actually, looked at this result a little bit already. We mentioned it earlier. And let's let P sub O of n be the number of partitions of n using only odd parts. And let's recall from what we just saw, we can write the generating function as this product as m goes from 0 to infinity of 1 over 1 minus q to the 2m plus 1. And then let's let P sub d of n, so these are the distinct parts, so that's the number of partitions of n with distinct parts. And again, from what we just saw, the generating function of this is the product as m goes from 1 to infinity of 1 plus q to the m. Now, this theorem that we're going to prove, which is due to Euler, is that the number of partitions with odd parts is equal to the number of partitions with distinct parts. And we'll prove this simply by showing these two generating functions are the same. But if these generating functions are the same, then when you expand them all out as power series, the coefficients of the power series are the same, but that gives us our result immediately. Okay, so let's start with the generating function for distinct parts. So I'm just going to copy it over here. We've got this product as m goes from 1 to infinity of 1 plus q to the m. And now what I'll do is I'll write out the first several terms here. So we've got 1 plus q, so those are our parts equal to 1. 1 plus q squared, those are our parts equal to 2. 1 plus q cubed, 1 plus q to the 4th, and since we've got space, 1 plus q to the 5th. And then that's going to extend on and on and on. And now what we're going to do is, well, multiply by a version of 1 that helps us manipulate this into the version we'd like to see. So what is that version of 1 going to look like? Well, we're going to have 1 plus q, and then I'm going to leave a little gap and have 1 plus q squared. I'll insert my version of 1 in these little gaps. So 1 plus q to the 4th, and then dot, dot, dot. I no longer have room for my 1 plus q to the 5th, but that's okay. Now I can put here in the middle 1 minus q over 1 minus q. I can put here in the middle here 1 minus q squared over 1 minus q squared, 1 minus q cubed over 1 minus q cubed here, and then 1 minus q to the 4th over 1 minus q to the 4th here. Okay, nice. But now I can do some grouping and multiplying out or expansion. So I'll group these two together, and that'll leave me with 1 minus q squared. I can group these two together. That'll leave me with 1 minus q to the 4th. I can group these two together. That'll leave me with 1 minus q to the 6th. And then finally, I can group these two together. That'll leave me with 1 minus q to the 8th. But now let's see what we've got. So in the numerator, I'll have 1 minus q squared times 1 minus q to the 4th times 1 minus q to the 6th times 1 minus q to the 8th, and so on and so forth. So I've got all of those even powers of q. And then in the denominator, observe that I've got all of the powers of q. 1 minus q, 1 minus q squared, 1 minus q cubed, 1 minus q to the 4th, 1 minus q to the 5th, and so on and so forth. But I think you can maybe see what's about to happen. We get some nice cancellation. So this 1 minus q squared will cancel this 1 minus q squared. This 1 minus q to the 4th will cancel this 1 minus q to the 4th. And then this 1 minus q to the 6th will cancel something down the line. Then this 1 minus q to the 8 will cancel something down the line. And well, what's left over? Well, exactly what we want to be left over, which is 1 minus q to odd numbers in the denominator. So I'll just write the first few out, but we've got this 1 minus q times 1 minus q cubed, and so on and so forth. But now we can package all these together into the product as m goes from 0 to infinity of 1 over 1 minus q to the 2m plus 1. But, well, we've done it. We've shown that these two types of partitions, types of restricted partitions, have the same generating function. But that means that there are an equal number of each of these types of partitions. So now what I'd like to do is see if we can push this a little further to discover our own identity. Okay, so let's explore a little bit. Let's say P1 of n is the number of partitions of n using odd numbers at most 3 times and distinct even numbers. And what we'll do is write down the generating function for this and then manipulate it into a form where we can read off another condition, and we'll insert that condition right here. We don't know what it is just yet. So let's first of all write out this generating function, which isn't too hard. So this is going to be the product as m goes from 1 to infinity of 1 plus q to the 2m minus 1. So that term corresponds to using the odd number 2m minus 1 one time, and then plus q to the 4m minus 2 plus q to the 6m minus 3. That corresponds to using that odd number 2 and 3 times. We're going to cut it off there because our rule says that we can use any odd number as many as 3 times. Then we're going to have times 1 plus q to the 2m. That corresponds to using distinct even numbers. And now, instead of multiplying by 1 here, we're going to use a standard formula for the sum of a finite geometric series. So this is a well-known sum. I'm not going to derive it or anything. You can look up the derivation if you'd like to. That says that 1 plus x squared ending at x to the k is equal to 1 minus x to the k plus 1 over 1 minus x. Okay, cool. So we've got this sum of a finite geometric series to use, and we can use that on both of these terms here. So we can use it on this first term, where x is equal to q to the 2m minus 1 and k is equal to 3. We can use it on this second term, where x is equal to q to the 2m and k is equal to 1. Okay, so let's see what that leaves us with. So we're going to have the product as m goes from 1 up to infinity of 1 minus q to the 8m minus 4. That's what we get for raising this to the 4th power, to the 3 plus 1st power, over 1 minus q to the 2m minus 1. And then that's going to be multiplied into 1 minus q to the 4th all over 1 minus q to the squared. Okay, so that's what we get from applying that formula as well. But now I'd like to observe something, and that is that these things in the numerator are the same. They're not always the same, but they're maybe what I would say often the same. So notice if m is equal to 1, that should have been a 1 there, an m there, and an m there. If m is equal to 1, we get 1 minus q to the 4th and 1 minus q to the 4th. So those line up. And then if m is equal to 2, we get 1 minus q to the 12th. And then if m is equal to 3, we get 1 minus q to the 12th. So those are going to line up as well. So that means sometimes we'll get cancellation of the things in the numerator and sometimes we won't. Now, instead of making like a verbal argument of why or which ones we want to cancel and which ones we don't, what I'll do instead is I'll write out a bunch of terms like this, and I think we'll intuitively know what to do. So this first term will be, what is it? 1 minus q to the 4th over 1 minus q. So that's the first term. The second term is 1 minus q to the 4th over 1 minus q squared. So that's from the m equals 1 case. Now from the m equals 2 case, we get 1 minus q to the 12 over 1 minus q cubed. And we get 1 minus q to the 8 over 1 minus q to the 4th. So that's from the m equals 2 case. From the m equals 3 case, we're going to get 1 minus q to the 20 over 1 minus q to the 5th times 1 minus q to the 12th over 1 minus q to the 6th. And since we've got room for 2 more, let's go ahead and write those down. So we're going to have 1 minus q to the 28 over 1 minus q to the 7 times 1 minus q to the 16 over 1 minus q to the 8, so on and so forth. And now we've just got to make a decision of which ones we cancel in the numerator and which ones we leave the same or leave without canceling. And you can choose one of 2 things, and you're going to get different partition identities in each of the cases. So we're going to make a choice to hold these that I'm boxing in yellow. So I'll just put hold here, as in we're not going to simplify. And so this is 1 minus q to the 4th power. And then this one down here, which is 1 minus q to the 12th power. And then, well, let's see. Notice that there's 3 between these 2 holds. So there's going to be 3 more, and then we're going to hold something that comes up later. And maybe I'll just stick that here. There is one thing between these 2, but the next one to hold is 1 minus q to the 20 over 1 minus q to the 10. So I'll just put in, we're going to hold this as well. There's a 1 minus q to the 18 type term, or to the 9 type term in the denominator between those two, but like I said, I'll leave that. And then after holding those, everything else in the numerator will cancel, and let's see that happen. So we've got 1 minus q to the 4th, canceling this 1 minus q to the 4th. We've got this 1 minus q to the 12th, canceling something that comes down the line. It's off the board, but it is there. We've got this 1 minus q to the 8, canceling this 1 minus q to the 8. Let's see, do we have anything else happening? Yeah, we've got this 1 minus q to the 20, canceling something down the line, and then these two get canceled by something down the line as well. But now let's rewrite this with everything that's left over. And what I'm going to do is I'm going to take these holds, or these things that I said to hold, and I'm going to rewrite them using our finite geometric series sum in reverse. So let's see, that means I can rewrite this as 1 plus q squared in the numerator. The next one that gets held is 1 plus q to the 6 in the numerator. The next one is 1 plus q to the 10 in the numerator. And then I'm going to leave myself a little bit more room in the numerator because we can guess the pattern here. What is the pattern? Well, notice these are all of the form 4n plus 2. They have a remainder of 2 when divided by 4. So that means this next one is probably going to be 1 plus q to the 14, and then 1 plus q to the 18, and so on and so forth. And then what's left over in the denominator? Well, notice that all of the evens in the denominator cancel, and we're left with simply all of the odds. So we've got 1 minus q, 1 minus q cubed, 1 minus q to the 5th, 1 minus q to the 7, and so on and so forth. So now we could package this together if we wanted to. This would be the product as m goes from 1 up to infinity of 1 plus q to the 4m minus 2 in the numerator, and then 1 minus q to the 2m minus 1 in the denominator. But now, using what we saw previously, we can rewrite this as a type of partition. So what would that type of partition be? Well, using our previous strategy, this is the number of partitions using distinct parts that are congruent to 2 mod 4 and any number of odd parts. Okay, so now that we've explored these basic proofs, I think it's time to start putting together what will be our proof of the Rogers-Ramanujan identities. Now that we've spent all of this time looking at how powerful generating functions are for proving partition identities, we should probably take a step back and remember that our final goal here is to prove these Rogers-Ramanujan identities. And now previously we looked at the partition version of these identities. And so now what we'd like to do is build that into the generating function version of those identities. And then, well, we can get to the proof. So let's recall that the partition form of the Rogers-Ramanujan identity is the number of partitions of n using parts that are congruent to 1 or 4 mod 5 is equal to the number of partitions of n whose consecutive parts differ by at least 2. So we started the video looking at examples of partitions of each of these types. And then, well, through what we just did with generating functions of partitions, we saw that this left-hand type, the congruent to 1 or 4 mod 5, kind of clearly has a generating function that is this left-hand side over here. So it's this product as m goes from 0 to infinity of 1 over 1 minus q to the 5m plus 1 times 1 minus q to the 5m plus 4. And now what we'd like to do is show that this right-hand part of the identity, the so-called difference 2 condition, has a generating function like this right here. So it's this sum as n goes from 0 to infinity of q to the n squared over 1 minus q times 1 minus q squared all the way up to 1 minus q to the n. And then, well, once we have shown that the partitions of this right-hand type, if you will, have this right-hand generating function, then we'll move to prove these two generating functions are the same. And, well, then we've got our identity. Okay, so let's look at this difference 2 condition generating function. And here I'm going to introduce some notation. Let's let A be all partitions satisfying this difference 2 condition. And now I'd like to observe that if lambda is in A, then that means that we can think of the partition like maybe lambda 1, lambda 2, all the way up to lambda k. So it's got to have a certain number of parts. We might as well say it has k parts. We're not going to worry about what it's a partition of. It's just a partition with k parts. But now let's look at our condition and see what that gives us. So I'm going to order these maybe in the opposite order that I had for my previous definition, but it's equivalent. So let's say that lambda 1 is bigger than or equal to 1. And then lambda 2 is going to be bigger than or equal to lambda 1 plus 2. That's because consecutive parts have this difference 2 condition. They differ by at least 2. And I'm ordering these, like I said, in the opposite order. So we have lambda 1 is less than or equal to lambda 2 is less than or equal to lambda 3, and so on and so forth. But notice that since lambda 1 is bigger than or equal to 1, that means lambda 2 is bigger than or equal to 3. Now let's look. Lambda 3 has to be bigger than or equal to lambda 2 plus 2, which means it's bigger than or equal to 5. And now you can maybe see what's going on here. Notice that if we follow this down, we'll have lambda k is bigger than or equal to 2 times k minus 1. So we've got that odd number there. But what does that mean? Well, that means that we can take our partition lambda 1 up to lambda k and rewrite it like this. We can say lambda 1 is equal to 1 plus mu 1. Lambda 2 is equal to 3 plus mu 2. All the way down, lambda k is equal to 2k minus 1 plus mu k. And well, the important thing here is that we have mu 1 is bigger than or equal to 0, but it's less than or equal to mu 2, less than or equal to mu 3, all the way down less than or equal to mu k. So let's observe that the mu may not be a partition like in the defining sense that we had before where we have positive integers, but we can still group it into a tuple. We can say mu is equal to mu 1 up to mu k. And well, it's not a partition with k parts. It's a partition with less than or equal to k parts. So why do I say less than or equal to k parts and not k parts? Well, that's because some of these may be equal to 0. Now, if none of them are equal to 0, it's a partition with k parts. If the first one is equal to 0 and then mu 2 and so on and so forth are bigger than 0, then it's a partition with k minus 1 parts, and so on and so forth. Notice that if they're all equal to 0, it's a partition with 0 parts, which is allowed. That's just the partition, the empty partition for the number 0. Okay, nice. And so now what I'd like to do is do this final calculation. We're actually ready for this final calculation. So let's say we've got this sum as n goes from 0 up to infinity of p sub 2 of n times q to the n. So I didn't introduce notation here, and I'm not going to write this down, but I'll just say that p sub 2 of n represents partitions satisfying this rule right here. And so that means p sub 2 of n would be this number of partitions of n whose consecutive parts differ by at least 2. Okay, and now here's the trick. We can write that as the sum, as k goes from 0 up to infinity, of the sum over all lambda inside of A of q to the lambda 1 added all the way up to lambda k. And so that's just another way of getting at all of the partitions satisfying our rule. But now, using this like little calculation exploration that we had over here, this is equal to the sum as k goes from 0 to infinity, and then the sum over these mu 1s up to mu k's of q to the 1 plus 3 all the way up to 2k minus 1 times q to the mu 1 added up to mu k. So that's just replacing the lambda 1 with 1 plus mu 1, the lambda 2 with 3 plus mu 2, and so on and so forth. And now here's a nice identity, which I won't prove here, but you can easily prove it with induction. And that is if you add together the first k odd numbers, so in other words, you add 1 plus 3 plus 5 all the way up to 2k minus 1, you get exactly k squared. And you can see that's true just by experimentation. Of course, that's not a proof, but you could maybe have some motivation for that being true. Like 1 plus 3 is equal to 4, that's 2 squared. 1 plus 3 plus 5 is equal to 9, that's 3 squared. 1 plus 3 plus 5 plus 7 is 16, that's 4 squared, and so on and so forth. Okay, but now what I'd like to do is bring this q to the k squared out. And so we'll have the sum as k goes from 0 to infinity of q to the k squared. And then I'm going to change this other sum, this inner sum, as follows. So I'm going to say mu, and this is a partition of less than or equal to k parts. And then we'll have q to the mu1 added all the way up to mu k. But now we're going to use this fact that we used when we were proving the generating function for the number of partitions in general, and that is the number of partitions of n with less than or equal to k parts is the same thing as the number of partitions of n whose largest part is less than or equal to k. And the number of partitions of n whose largest part is less than or equal to k has a generating function that we wrote down before. And so that allows us to do that. So let's have the sum as k goes from 0 up to infinity of q times k squared. And then that's going to be multiplied into 1 over 1 minus q times 1 minus q squared, ending at 1 minus q to the k. But now we're essentially done. We put that q to the k squared in the numerator, and then we can re-index the k back to an n, and it looks exactly like the right-hand side of this. Okay, so that's good. So now I think we've motivated why this partition form of the Rogers-Ramanujan identity is equivalent to this generating function form of the Rogers-Ramanujan identity. And now we're almost ready to jump into the meat of the proof. But before we do that, I'd like to go over some of the history of this identity. Now that we've seen the partition version, as well as the generating function version of the Rogers-Ramanujan identity, we're now going to look at an incomplete timeline of these identities. And so I'd like to point out that this is incomplete, but I think we do hit the high points. And it's 1894 that these identities were first discovered and proved by Rogers. And so you can see this little clip of his paper, and let's observe that the notation is, well, it bears some resemblance to what we have with our Q series or our generating functions, but it is like a little old-fashioned compared to what we use today. Then moving on, in 1913, these identities were rediscovered without proof by Ramanujan. And so these were the first 2 times that these identities were discovered, which is, I think, probably why we call them the Rogers-Ramanujan identities. Although, as we'll see in just a bit, sometimes they're given a third name as well. And so in 1917, these are rediscovered with proof by Schur. And that's where I'd like to point out that, yes, these sometimes are called the Rogers-Ramanujan-Schur identities. And I guess it's interesting to see that Schur had a proof for these identities, and so did Rogers, but originally Ramanujan did not provide a proof for these identities. That being said, in 1919, there was a new joint proof published by Rogers and Ramanujan. And you can see that the notation here is a little bit closer to what we've been using. And that's because the notation we've been using is inspired by the notation used very commonly by Ramanujan. Now let's jump all the way to 1966, when George Andrews provided an analytic proof of these identities. And similar to many mathematicians, Andrews is captivated by these identities. In fact, he's published more than 20 proofs of the identities throughout his career. Now, moving on to 1981, we have the first vertex algebraic interpretation and proof by Lepowsky and Wilson. And so Lepowsky and Wilson were instrumental in the early days of using vertex algebraic techniques to study modules of affine Lie algebras. And well, that's what they did here. They used these vertex algebraic techniques to study the affine Lie algebra attached to SL2 and its modules. And as you can see, the paper says a Lie theoretic interpretation and proof, but that's because vertex algebras were not widely studied in the early 80s. And since Lepowski has pointed out that this is more of a vertex algebraic proof and not a Lie theoretic proof. Now, also in 1981, a bijective proof was given by Adriano Garcia and Stephen Milne. So what's interesting about a bijective proof is it doesn't involve any of the generating functions. So the proof that we'll present will involve the generating functions, as we've kind of outlined already. But this proof simply takes the set of partitions where the difference between consecutive parts is at least 2 and finds a bijection to the set of partitions where the parts are congruent to 1 mod 5. So no generating functions at all. Now, moving on to the year 2000, Jason Fullman presented a probabilistic proof of the Rogers-Ramanujan identities. So these involved Markov chains. And if you're keeping track, this is the 4th very different proof technique used to prove these identities. So we have a straightforward calculation involving the generating function. So those are probably most of the proofs. Then we have our bijective proof, and then we have our vertex algebraic proof, and now finally we've got this probabilistic proof. So I think it's really interesting to see that these identities can be proven by many, many different methods. So as was hinted at with Lepowski and Wilson's paper, these identities have connections with vertex algebras, and Mirko Primps in fact, has spent a lot of his career taking Rogers-Ramanujan-like identities and giving them interpretations inside of vertex algebras and the combinatorial identities that are within the structure of these vertex algebras. And so I think maybe the first of his paper to do this kind of thing was in 2002. Now, in 2003, my PhD advisor, Anton Milas, gave a connection to the Virasoro algebra. So the Virasoro algebra is a certain Lie algebra, and it and its representations form an important part of modern physics, maybe theoretical physics, including maybe a subject known as conformal field theory. And in fact, every vertex operator algebra has a copy of the Virasoro algebra inside of it. So this Virasoro algebra can really be seen as a very important universal object. And the fact that this very important universal object has some sort of relation to these identities really just points towards these identities having some sort of universality to themselves. And now, together with Kalinescu, Lepowski and Milas discovered a relation of the Rogers-Ramanujan identities and so-called principal subspaces of the standard modules for affine Lie algebras. So in fact, my PhD thesis involved a study of principal subspaces and principal subalgebras of so-called lattice vertex algebras. And a lot of the techniques that were used in this work, as well as the first several of my publications, were introduced in this first paper by Kalinescu, Lepowski, and Milas. Now, moving to our most recent result, in 2022, Rosengren presented a simplification of Rogers' original proof. And in fact, the proof we'll present has some similarities with this proof of Rosengren, as well as the so-called motivated proof given by George Andrews. Okay, so now with all of that background behind us, we're finally ready to look at the technical details of the proof of these identities. We've got a bit of a slog for a complete proof of the Rogers-Ramanujan identity, so I thought we'd start with an outline. So the first thing that we're going to do is look at 2 preparatory lemmas, and these lemmas are due to Euler. Then we'll use these lemmas to prove something called the Jacobi triple product identity. Then we'll use the Jacobi triple product identity to prove a pretty technical step. Now, the technical step isn't really going to be super motivating, but a pretty simple application of this technical step will give us the final step of our proof, which will give us the result that we're looking for. Okay, so now that we've seen this outline, let's jump into the first of our preparatory lemmas. Let's look at a lemma that's due to Euler that'll help us prove the Jacobi triple product. So what we have is for all z and q, whose absolute value, or modulus if you think of them over the complex plane, is less than 1, we have this sum as n goes from 0 to infinity of z to the n over 1 minus q times 1 minus q squared all the way up to 1 minus q to the n is equal to this product as m goes from 0 to infinity of 1 over 1 minus z times q to the m. So this is an example of a sum to product identity. And well, we're going to be looking at several of these. In fact, the whole goal of this is to prove the most famous, or one of the most famous of these sum to product identities, the Rogers-Ramanujan identity. Okay, so let's get to it. So we're going to start off by defining this right-hand side to be this function f of qz. So this is the product as m goes from 0 up to infinity of 1 over 1 minus z times q to the m. So like I said, just the right-hand side. Okay, and then from there, what I want to do is define a family of functions of q. So I'll call this family a sub n. And here we're going to have n bigger than or equal to 0 by the following. So we'll have f of qz is equal to the sum as n goes from 0 up to infinity of a sub n of q times z to the n. So in other words, what we want to do is think about this thing right here, this product, which we've labeled as fqz, and expand it as a power series in z. But if we expand it as a power series of z, well then those coefficients will depend on q. And we're just defining those coefficients to be these functions a, n, q. Okay, great. And now, well, now we're going to start making some observations about the structure of this fqz. Okay, so let's maybe start with the following. So let's observe that if we take f of q and then zq, so in other words, what we're doing is replacing q with itself, so q with q, and then we're replacing z with z times q. So that's going to give us this product as m goes from 0 up to infinity of 1 over 1 minus z times q to the m plus 1. Okay, great. But now let's observe the following. So this is an infinite product, and where does it start? Well, observe that it starts at 1 over 1 minus z times q. And then after that, we have 1 over 1 minus z times q squared. After that, 1 over 1 minus z times q cubed, and so on and so forth. Great. But now what I'd like to do is multiply by a special version of 1. And that version of 1 is 1 minus z over 1 minus z. Okay, but now we can take this 1 minus z out front, the one that's in the numerator, and then rewrite the rest of it as, well, a new infinite product. And I'm going to use the same index here because I don't think it's super confusing, but we'll take the product as m goes from 0 to infinity of 1 over 1 minus z times q to the m. But now let's observe that this product that we just built is exactly our original definition of this fqz. So here we have this is 1 minus z times our f of qz. Great, and so, well, let's maybe underline where we started and where we ended here. And this is like a nice functional equation, if you will, for this fqz function. But now what I'd like to do is take that orange underlined functional equation that we built and put it in terms of these a sub n of q's. Okay, so let's maybe see how that'll go. So let's start with this 1 minus z times our fqz, but we'll use this version of our fqz expanded with these a n of q's. So we've got our sum as n goes from 0 up to infinity, a n of q times z to the n. Okay, so we know that that's equal to what? Well, that's equal to this f of qz zq, but we can get that by replacing every z here with a z times q. So that's going to look like this. We'll have our sum as n goes from 0 to infinity, a sub nq, and then we'll have q to the n, z to the n, because we replaced z with q times z. I think that's pretty clear. Then next up, what we'll do is take this 1 minus z and multiply it through on the left-hand side. So that'll leave us with a sum as n goes from 0 to infinity of an of q times z to the n. That's the first term. And then minus the sum as n goes from 0 to infinity of an of q z to the n plus 1. That's the second term. And then the last thing that we'll do here before moving on is let's take this second sum that we have here and re-index it a little bit. So let's re-index it by taking every n that we see and replacing it with n minus 1. So that's going to turn this into the sum as n goes from 1 to infinity. Because here we have n starting at 0, but that means our new n minus 1 starts at 0, which means our new n starts at 1. And then we'll have a sub n minus 1 of q times z to the n. Okay, great. And then, well, let's maybe underline what we have so far. So we have this pink underlined right-hand side of the equation is equal to this thing that we have here, arc underlined in pink, minus this thing over here, which we got from re-indexing. So let's start the top of the next board with that equation. Here's where we ended up on the last board. So I did group two things that were on the left-hand side of the equation together into one sum. And then I reordered some of the stuff on the right-hand side of the equation. So now we've got this sum as n goes from 0 to infinity of an of q minus an minus 1 of q, all times z to the n, is equal to this sum as n goes from 0 to infinity of q to the n, an q, times z to the n. And here, observe that there's something a little bit problematic when n is equal to 0. We get a sub minus 1. And observe in our original definition over here, we didn't have a definition of a sub minus 1. But let's go ahead and set it equal to 0. Just, that fixes everything, if you will. Okay, great. But now what we'll do is look closely and notice that this stuff that I'm underlining in magenta on the left-hand side of the equation is the coefficient of z to the n. And this stuff that I'm underlining in the same color on the right-hand side of the equation is the coefficient of z to the n on the right-hand side of the equation. So now what we'll do is extract the coefficient of z to the n from both sides of the equation. And what that'll give us is like a new, maybe, system of equations for this function a sub n of q. So for n bigger than or equal to 0, now we have anq minus an minus 1 of q is equal to q to the n times an of q. Oh, I think that's looking pretty nice. Now what we could do is pretty easily solve that for an of q. So we'll have an of q minus q to the n an of q is equal to an minus 1 of q. But in turn, what we can do is factor an a sub n of q from the left-hand side of the equation, and we're going to be left with, well, let's really spell this out. So here, factoring this a sub n of q out, we'll have 1 minus q to the n times a sub n of q. Then we can divide both sides of this equation by 1 minus q to the n, leaving us with a really important recursion, if you will. So we have a sub n of q is equal to an minus 1 of q all over 1 minus q to the n. And I should point out here that this works only if n is bigger than or equal to 1. This breaks down here if n is equal to 0 because we get a sub minus 1, but also we're dividing by 0 in that case as well. But now what we can do is like continually apply this recursion. So notice now we could write this as a sub n minus 2 of q over 1 minus q to the n minus 1 times 1 minus q to the n. And then, well, we can keep doing this on and on and on. And what we'll end up with is a sub 0 of q over 1 minus q times 1 minus q squared all the way up to 1 minus q to the n. Nice. But now all we have to do is figure out what a sub 0 of q is. But let's observe that what we have here is a sub 0 of q is, well, it's the constant term from this expansion. But I think it's pretty easy to see that the constant term from this expansion is equal to 1, given the fact that you expand each of these as geometric series. So let's insert that. So we have this, a sub 0 of q is in fact simply equal to the number 1. But let's see what that leaves us with. We have a sub n of q is equal to 1 over this rising product, 1 minus q, all the way to 1 minus q to the n. But if we look at that closely and put it into our equation over here, we see that we've created exactly this left-hand side of the equation. But since f of qz is the right-hand side of the equation, we've finished the proof of this lemma. Now we're going to look at a second lemma that'll again help us prove the Jacobi triple product identity. And this one can be seen as like sort of a reciprocal result to our previous lemma. So here we've got the sum as n goes from 0 to infinity of q to the n times n minus 1 over 2 times minus z to the n over 1 minus q times 1 minus q squared all the way up to 1 minus q to the n is now equal to the product as m goes from 0 to infinity of 1 minus z times q to the m. So let's observe that before this term was in the denominator of the right-hand side, and also this left-hand side looked quite a bit different. The only thing in the numerator before was z to the n. So I'm going to wave my hands at parts of this proof because it's very, very similar to what we did before. So we're going to reuse our function name, capital F, but now it's going to be for this right-hand side. So again, we're letting capital F of qz equal this product. And then we'll expand that as a power series in z, meaning the coefficients are functions of q. We'll name them a sub n of q again. And then as a little exercise, you can prove that f of qz is equal to 1 minus z times f of qz. So again, that's a little bit different than the one that we had before, but that's what'll help us here. And now let's observe that under this setup, what we'd like to do is prove that a sub n of q is equal to minus 1 to the n times q to the n times n minus 1 over 2 over, well, that rising product from 1 minus q to 1 minus q to the n. Okay, so how might we do this? Well, let's start off with this f of qz term, and we're going to write that as the sum as n goes from 0 to infinity of a sub n of q times q to the n. But of course that needs to be equal to this 1 minus z times f qz. So let's write that out. We have 1 minus z, and then the sum as n goes from 0 up to infinity. Oh, and I just realized this should have been a z to the n here. And now this will be q to the n, a n q times z to the n. Okay, great. But next up, what we'd like to do is multiply out this right-hand side as we did before. So quickly, that's the sum as n goes from 0 to infinity, qn, an, q, z to the n. And then that'll be minus this sum as n goes from 0 to infinity of, let's see, q to the n, an, q, z to the n plus 1. But now what we'll do is re-index this term that I'm underlining in peach to give it a power that is z to the n instead of z to the n plus 1. And you can do that by replacing all of the n's with n minus 1s just like we did before. So here we're going to have this is the sum as n goes from 1 to infinity, q to the n minus 1, a n minus 1 of q times z to the n. Okay, good. And then next up, what we'll do is take this thing that I have over here on the right-hand side, underlined in yellow, move it over to the left-hand side, combine those two terms, and then we've got something we can work with. So here, combining those two terms, we have the sum as n goes from 0 up to infinity of 1 minus q to the n times a sub n of q times z to the n is equal to this sum as n goes from 1 to infinity of minus q to the n minus 1, a n minus 1 of q, and then z to the n. Okay, great. And then from here, we're going to do, well, the standard thing that we've done a couple of times already, and that is extract the coefficients of z to the n from both sides of this equation. So keeping in mind that this is only going to work for certain values of n and so on and so forth, I guess n needs to be bigger than or equal to 1. That's our only restriction. So observe that's going to give us something like this. So we'll have a n q is equal to minus q to the n minus 1 over 1 minus q to the n times a n minus 1 of q. But now, well, we're going to reuse this recursion over and over and over again until we get down to a0 of q. And that's going to be something like this. We'll have minus q to the n minus 1, minus q to the n minus 2, all the way down, minus q squared minus q, all over 1 minus q to the n multiplied down to 1 minus q. And then this is all times a sub 0 of q. But again, looking at this, a sub 0 of q is the constant term from this expansion of the right-hand side, which is pretty clearly equal to 1. So we'll just take this and replace it with the number 1. But now let's see what we've got here. If we multiply out this numerator, we're going to have a minus 1 to the n. That's because I left off a extra minus 1 term at the end, so just keep that in mind. So there are n terms in the numerator. Each is attached to a minus sign. That'll give us a minus 1 to the n. And then we'll have q to the n minus 1 plus n minus 2 plus all the way down plus 2 plus 1. Just using our rules that take products of things with exponentials to sums. And then this is all over 1 minus q to the n multiplied all the way down to 1 minus q. But now let's observe that this sum, n minus 1 plus n minus 2, all the way down plus 2 plus 1, is exactly equal to this n times n minus 1 over 2, because of course this is a very famous triangular number, and well, the triangular numbers have well-known forms, and they're like this over here. I think that's pretty well known. Okay, so there we have it, the proof of our second preparatory lemma for the Jacobi triple product identity. So now we're ready for the proof of the Jacobi triple product identity. So let's look at what this identity says. So on the left-hand side, we have a sum term. It's the sum as n goes from minus infinity to infinity of q to the n squared times z to the n. And then on the right-hand side, we have a product term. So we have the product as m goes from 1 to infinity of 1 minus q to the 2m times 1 plus q to the 2m minus 1 times z times 1 plus q to the 2m minus 1 times z to the minus 1. And then, well, in order to have these on the board as we use them, here are the lemmas that we just proved. So I'll call this one the blue dot lemma, and then we have the peach dot lemma. Okay, so let's start with this term right here, which notice that is part of the product on the right-hand side. It's this central term on the right-hand side. And well, we're going to start with a very, very trivial first step, and that's going to be a reindexing step. So I'm going to reindex this, so I start at m equals 0. So if you like, that means that we're going to replace all of the m's with m plus 1s. That moves our starting point down from 1 to 0. And then we're going to have 1 plus z times q to the 2m plus 1. Okay, great. And now, well, let's rewrite this product in a way so that it's obvious that we can use one of our lemmas. So here we've got this product as m goes from 0 to infinity. And then we'll have 1 minus, so something crazy is going to play the role of z. We're going to have minus z times q. And then that's going to be times q squared to the m power. So now observe that we have something that looks like the right-hand side of our blue dot identity, where z has been replaced with minus zq, and q has been replaced with q squared. So let's color code that right here. So we've got blue dot with, like I said, q is replaced with q squared, and z is replaced with minus zq. Okay, good. But now that means that we can apply this identity as long as we rewrite the sum side using our obvious replacements that we've made. Okay, so now this is going to be the sum as n goes from 0 to infinity of, well, notice we'll have q squared raised to this power over 2, but the 2 from the q squared and the 2 in the denominator will cancel, leaving us with q to the n times n minus 1 in the numerator. And then over here we'll have what? Well, it's going to be 1 minus q squared multiplied to 1 minus q to the 2n. So that takes care of our q replacement. And now let's make our z replacement. So we're replacing z with minus z times q. Well, that's going to get rid of this minus sign, and we'll be left with a q to the n times a z to the n as we distribute that, nth power to the q and to the z. Okay, so I think that's looking pretty good. But now we can do a quick step where we take this q to the n here and combine it with this q to the n times n minus 1 and gives us a q to the n squared. And then what I'd like to do is, well, extend this finite product in the denominator to an infinite product in the denominator. But I can do that by multiplying something in the numerator. Okay, so, well, let's get that going. So that's going to give us something like this. So we'll have the sum as n goes from 0 to infinity of qn squared times z to the n. And then in order to complete that denominator, I'm going to have this product 1 minus q to the 2n plus 2, 1 minus q to the 2n plus 4, the product going on and on and on. But that's going to complete this to an infinite product in the denominator, which now it won't have anything to do with n, so I can factor it out. And I'll factor it out, and I'll write it as the product as m goes from, let's see, 1 to infinity of 1 over 1 minus q to the 2m. Okay, nice. Okay, well, look at what we've got here. We've got this product of our 1 over 1 minus q to the 2m term here, and we've got this term right here. Well, notice if I multiply both sides by the reciprocal of this product, I have two parts of my triple product identity. So let's go ahead and write that down. So now we have the product as m goes from 1 to infinity of 1 minus q to the 2m times 1 plus z times q to the 2m minus 1 is equal to this sum as n goes from 0 to infinity of q to the n squared times z to the n, and then times the product as, well, let's see what it's going to be. K is going to go from n plus 1 up to infinity of 1 minus q to the, that'll be 2 times k. So just to be clear here, that is capturing this infinite product here that we made out of the dot, 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 if you will. Okay, so I'm going to do one more thing before we're moving on to the next step at the top of the next board, and that is to notice that if we take this product right here, which is at the tail end of our, equation at the moment, and we think about what that would be with negative values of n. So if n is equal to -1, then we have k equals 0, but that gives us 1 minus q to the 0, which is 1 minus 1, or in other words, 0. And that happens if n is equal to -1, and something similar happens if n is equal to -2, and so on and so forth. So in general, this whole thing is equal to 0 when n is less than 0. So that means, well, we can simply add all of those back in and change this from a sum from 0 to infinity to a sum from -infinity to infinity. Because in fact, we're just adding 0 into this sum infinitely many times because of how that product collapses. Okay, so now let's move what we've got to the top of the next board and then keep going. Okay, so here's where we just ended up. And now what I'll do is I'll take this product that's inside of the sum on the right-hand side, and what I'm going to do is re-index this. And I'd like to re-index this so that the product starts at 0. Because if we've got the product starting at 0, perhaps it'll look like, well, the right-hand side of this blue dot equation. And the way to do that is to take all of the k's and replace them with k plus n plus 1. Because if k plus n plus 1 is equal to n plus 1, then k is equal to 0. Okay, so let's see what that's going to leave us with. So I'm going to copy down a bit. So this sum is n goes from -infinity to infinity, q to the n squared, z to the n. And now, like I said before, I've got this product as k goes from 0 to infinity, as was my goal. And then I'll have 1 minus q to the 2k plus 2n plus 2. But I'm going to break that apart into q to the 2k times q to the 2n plus 2, like that. Okay, but next up what we're going to do is apply our product formula, our blue product formula again. So in this case, we're going to apply it with what? So q is replaced again with q squared. So that's going to gobble up this q to the 2k. And then z will be replaced with q to the 2n plus 2. That's going to, well, obviously gobble up this q to the 2n plus 2. And now observe that it looks exactly like this, but it's just the index we're using is k instead of n. Okay, so bringing some stuff down, we've got this doubly infinite sum, which, like I said, I'm just going to bring down. And then using this sum to product identity now, we have the sum as, well, I need a new index now. I'm going to use r. So r will go from 0 to infinity. And then what are we going to be left with? Well, we're going to be left with q to the r times r minus 1. That's from this numerator here where q is replaced with q squared, just as we saw before. And then this is going to be all over this product 1 minus q squared all the way up to 1 minus q to the 2r, similarly to before as well. And then next up we'll have minus q to the 2n plus 2 all raised to the r power. So something like that. But now what can we do from here? Well, a lot of it is just bringing stuff down, and then what we'll do is smash together everything that's happening with the exponent of q in the numerator of this second sum. So what's that going to look like? Well, we're going to have a minus 1 to the r, so let's go ahead and write that down. And then we'll have a q to the r squared, so that's from this first term. And observe that we're going to have a q to the minus r here, and then a q to the 2r there. So that'll give us a q to the r, which we can just write as a plus r happening on, like that. And then also a plus n, q times n times r. That comes from the second term. Okay, then we can just take the denominator and bring it down. So that's this rising product, 1 minus q squared up to 1 minus q to the 2r. Okay, so now let's move on from here. Okay, so this is where we just ended up. And now, before we write the next step, I'd like to notice one kind of pretty important thing. And that is what we would have if we were to put all of the q's together and view this as like a double sum instead of these iterated sums. So observe we have q to the n squared plus 2nr plus r squared plus r. But that n squared plus 2nr plus r squared will factor. And it'll in fact factor to n plus r squared. And then we've got that extra plus r on, as needed. Okay, and then that motivates us to split this into two pieces. And I'm going to change the order of summation while we're at it. So we're going to have the sum as r goes from 0 up to infinity. And now I'm going to write something down that's a little bit crazy, but we'll talk through how it all simplifies to what we had before. So minus q times z to the minus 1 all raised to the r power over 1 minus q squared all the way up to 1 minus q to the 2r. So that's my first bit. And then the sum as n goes from minus infinity up to infinity of q to the n plus r squared times z to the n plus r. Okay, so let's see why that works. So here we've got our q to the n plus r squared and then another q to the r here. So we achieve that orange boxed q term. And then notice here we've got a z to the n plus r. Here we have a z to the minus r. So put together, that's going to achieve this z to the n term. And now what we'll do is finally use this peached dot equation, that we actually proved first among these two. And we're going to use that for this first term. So let's maybe write it out here. So we're using this peached dot equation where we replace q with q squared. And then we're going to replace z with minus q times z to the minus 1. Okay, so let's bring that down and see what we have. Okay, so making that replacement, we'll have this product, and I'm going to reindex this at the same time. So it's going to be the product as m goes from 1 up to infinity of 1 over 1 plus z to the minus 1 times q to the 2m minus 1. Like I said, I did a re-indexing step at the same time, but I think you could work that out. That'd be a nice exercise if you wanted to work out that step that I left. And then I'm going to do a re-indexing step on this equation that I'm underlining, or this term that I'm underlining in green here. I'm going to replace all the n's with n minus r's. But since I'm summing over all positive integers, my, summation will not change what I'm summing over. It's still all possible integers. It's just now everything simplifies and we have the sum as n goes from minus infinity to infinity of q to the n squared times z to the n. Okay, great. But now let's look at what we've got here. So we've got this thing that I'm underlining in orange multiplied by this term is equal to this double product over here. But if we were to multiply the reciprocal of our first term into the left-hand side product, we would achieve exactly the right-hand side of our Jacobi triple product identity. Furthermore, we would just leave this right-hand side exactly with what we need for the left-hand side of the Jacobi triple product identity. Okay, so that finishes the proof of this very important identity. Now that we've proven the Jacobi triple product, we're ready to apply it. And we're going to apply it to this function that comes out of nowhere. But this function and its relatives, which we'll look at in just a bit, will be very important for the most technical part of our proof. Okay, so let's look at this function. It's f1 of z, and that's equal to the sum as n goes from 0 to infinity. In the numerator, we've got a lot, but let's look at just one piece at a time. We have minus 1 to the n times z to the 2n times q to the n times 5n plus 1 over 2, and that's times 1 minus z squared times q to the 4n plus 2. And then in the denominator, we've got this rising product, 1 minus q all the way up to 1 minus q to the n. And then we pick up with an infinite product, and that's the product as k goes from n plus 1 to infinity of 1 minus z times q to the k. Okay, so the first thing that we want to do is look at what happens when we plug in z equals 1. And this is going to be maybe one of the most important things about this function. So you might say, well, if we're going to plug in z equals 1 and get something nice out of that, well, why do we need this new variable z in here? Well, as we'll see, we'll need this new variable z for the technical step. Okay, so plugging in 1, we get the following. So we're going to have this sum as n goes from 0 up to infinity. And then we'll have minus 1 to the n. Well, that z to the 2n is clearly just going to be 1. And then we have q to the n times 5n plus 1 all over 2. And then here we have 1 minus q to the 4n plus 2. And then this is all over 1 minus q times all the way up to 1 minus q to the n. But next up, what I'll do is, instead of writing that as an infinite product with product notation, I'm just going to pick up and notice when z is equal to 1, the first term of this is 1 minus q to the n plus 1. And then we have 1 minus q to the n plus 2, and then that's going to continue forever. So plugging in z equals 1 completes this denominator into an infinite product. And that's where we're going to pick up over here with that factored out. So we've got f1 of 1 is, let's see, this product as k goes from 1 to infinity of 1 over 1 minus q to the k. Like I said, that's factoring out this denominator. And then, well, I'm going to split this numerator part into two sums. One sum where you multiply this through to the number 1, and the other where you multiply through to the rest. Okay, so we've got our sum as n goes from 0 up to infinity, minus 1 to the n, q to the n times 5n plus 1 all over 2. And then from that, we will subtract the sum as n goes from 0 to infinity, another minus 1 to the n. And now we'll have a q to the n, 5n plus 1 over 2 times a q to the 4n plus 2. Okay, so something like that. Okay, and then next up what we'll do is maybe we'll perhaps bring this minus sign in here, and we'll change that n to an n plus 1. Or actually, we're going to change it to a minus n plus 1, because minus n plus 1 and n plus 1 will have the same parity. Thus, they'll create the same like positiveness and negativeness. Okay, great. Then next up, what we'll do is re-index this second sum. And we'll re-index this by taking all of the n's and replacing them with minus n minus 1. Okay, so now bringing that down, what do we have? Well, now we've got this product k goes from 1 to infinity, 1 over 1 minus q to the k. That's just coming down for free. And then this first sum is also coming down for free, so I'm just copying that down. We still have this q to the n times 5n plus 1 all over 2. And then, well, what's going to go on with the rest of this? Well, if we re-index this where n is being replaced with minus n minus 1, notice when minus n minus 1 is equal to 0, n is equal to negative 1. And then as minus n minus 1 approaches infinity, n is going to approach negative infinity. So in fact, this turns in to the sum as n goes from minus infinity to minus 1, if you will. And then we're going to have a minus 1 to the n here. And that's, well, simply because of how we re-indexed. If we replace n with minus n minus 1 here, observe that the plus 1 will get canceled out. And then, well, what happens with the rest of this? Well, you can plug all of this into what we have up here, and you'll observe that it factors back out exactly the way we have it. So n times 5n plus 1 all over 2. It's just we're missing this q to the 4n plus 4. And that's actually why, or q to the 4n plus 2. And that's why this thing is constructed the way it is over here. So that's kind of the magic of all of this. But now let's observe what we have. We've got a sum from 0 to infinity and then minus infinity to -1 of the same object. But that means we really have a sum from minus infinity to infinity. So let's take this and bring it down. So we've got this product, k goes from 1 to infinity, 1 over 1 minus q to the k. And then our sum, as n goes from 0 to infinity, minus infinity up to infinity of, now I'm going to write this kind of in a crazy way. I'm going to write this as, let's see, a q to the power 5 halves, all raised to the power n squared. And then I'm going to write this next part as a minus q to the half, all raised to the power n. Okay, but notice if we were to rewrite this, this term over here that I'm overlining in green would coincide with this thing that I'm underlining in green here, which of course exists over here as well. Oh, and that should gobble up the minus sign as well. But why did I write it like this? Well, I wrote it like this so it would look exactly like this left-hand side of the Jacobi triple product identity. And in fact, it does look exactly like that. So now we're going to use the Jacobi triple product with the following substitutions. I think they're pretty clear based off of how I wrote this. We'll make replacements of q with q to the 5 halves and z with negative q to the half. Okay, so let's see what that's going to leave us with. But as I do that, I'm going to combine it with this product that we have here. So we're writing this sum as a product. We might as well write this part as a product as well. Okay, so I'm going to reindex a bit, and I'm going to start this at m equals 0 and then go to infinity. And then, well, what's that denominator going to be? Well, observe that this denominator is taking the product over all natural numbers. So we have 1 minus q squared, 1 minus q cubed, so on and so forth. But I'm going to rewrite that as 1 minus q to the 5m plus 1, and then 1 minus q to the 5m plus 2, and then 1 minus q to the 5m plus 3, and then 1 minus q to the 5m plus 4, and then 1 minus q to the 5m plus 5. Okay, so now let's observe that that captures everything that's happening in this first product, just maybe in chunks of 5. Okay, and then while applying the Jacobi triple product here, what will we have? Well, let's see. This 1 minus q to the 2m will turn into a 1 minus q to the 5m plus 5. I'm like simultaneously re-indexing this to start at 0 instead of starting at 1, but I think that's okay. And then let's see. This 1 minus q to the 2m minus 1 times z, well, that's in fact going to turn into 1 minus q to the 5m plus 3. Again, with my simple re-indexing. And then, well, this last term, this 1 plus q to the 2m minus 1 times z inverse will be 1 minus q to the 5m plus 2. Again, with the re-indexing. But now let's observe that some stuff cancels. This term cancels with this term, the 5m plus 5 terms. In other words, the product over multiples of 5. The products over multiples of, or not multiples of 3, but things of the form 5n plus 3 cancel each other. And then finally, the things of the form 5m plus 2 also cancel each other. But then, writing that over here, we've got this product as m goes from 0 up to infinity of, now it's 1 over 1 minus q to the 5m plus 1 times 1 minus q to the 5m plus 4. which is, well, that's exactly the generating function for partitions that use parts of the form 5m plus 1 and 5m plus 4, which of course is, well, one side of our Rogers-Ramanujan identity. So it turns out that this fancy function here, when specialized to z equals 1, and after applying the Jacobi triple product identity, will give us this nice product side of the identity that we're trying to prove. Okay, so now what I'd like to do is introduce some maybe relatives of this function, and then we'll produce another really important identity that these functions satisfy. Okay, so let's get to that. Okay, so here are those companion functions. So it's a whole indexed family of functions. So there's a lot going on here. We'll call these fi of z, and it's this sum as n goes from 0 to infinity again. We have a minus 1 to the n, z to the 2n, so that's kind of the same. Now we have q to the n times 5n plus 3 over 2 minus I times n. So observe if you set I equal to 1, we get that n times 5n plus 1 over 2, just like we had before. And then all of that is multiplied into 1 minus z to the I plus 1 times q to the 2n plus 1 times I plus 1. Again, if you set I equal to 1, you retrieve this entire numerator that we had for our f sub 1 of z function. And then the denominator is exactly the same. It does not depend on the index I. So we just got done proving that f sub 1 of 1 was equal to, well, it was equal to the product side of our Rogers-Ramanujan identity. Okay, so let's maybe see what we can do with this family of functions. And the idea here is to look at this like difference equation that this family of functions satisfies, but we need to build that. So here we have f sub I of z minus f sub I minus 1 of z. So this is what we're going to look at first. And maybe I should point out that this proof is taken from George Andrews' number theory book. That being said, it's pretty close to Ramanujan's original proof, which can be found in a nice book called The Invitation to the Rogers-Ramanujan Identities. Okay, so let's see what we'll get from this. So I'm going to go ahead and put this together into a single sum that we can work with. So it's going to go from 0 to infinity, and let's like write down all of the stuff that's not going to change first. So that'll be our minus 1 to the n, our z to the 2n, and then our q to the n times 5n plus 3 all over 2. And then here we also have a q to the minus in, but that's going to change as I switches to I minus 1 here. So we're going to actually group all of the rest of the terms in these parentheses. So we'll have a q to the minus in. So that's from the f sub I of z term multiplying into this number 1 right here. Okay, and then next up we'll have minus z to the I plus 1 times q to what? Well, it's going to be 2n plus 1 times I plus 1, and then minus in. So again, that comes from this f sub I of z, where this q to the minus in multiplies into the second term. Okay, and then we're going to have two terms here connected to the f sub I minus 1 of z. And they're going to be, well, essentially just copies of this. So since we're subtracting, the sign is going to switch. So we have minus q to the minus I minus 1 times n. And then plus, it'll be z. Now it's to the I power. And then we'll have a q to the 2n plus 1. Now that's simply times I. And then minus I minus 1 times n. And then, well, all of this is over our denominator that's just going to stick around. So 1 minus q multiplied all the way up to 1 minus q to the n, and then we have this infinite product. So it starts at n plus 1, goes to infinity, 1 over 1 minus, or sorry, that's not in the denominator, 1 minus z times q to the k. And then, well, the trick here is to split this into two pieces. And, well, it's not the original two pieces. They're kind of like interwoven pieces. So I'll color code it. So I'll take this yellow underlined term and this yellow underlined term, and I'll put them together. And then I'll take this blue underlined term and this blue underlined term, and we'll put those together. And then, well, we'll factor out as much as we can from each of those terms. Okay, so let's start with the yellow underlined term. So that's going to be our first sum. That's going to go, again, from 0 to infinity, minus 1 to the n. I'm just copying down all of the stuff that doesn't change first. So, I mean, a lot of stuff is not changing, so that's kind of a chore. And then, well, from this yellow underlined stuff, I can factor out a q to the minus I times n, and I'm left with, well, what am I left with? 1 from factoring out of this first term, and then minus q to the n from factoring out of this second term. If we were to distribute that minus sign through, it would be minus I times n plus n. Okay, so that's nice. That's how that goes. And then I've got this same denominator. So I've got my product 1 minus q all the way up to 1 minus q to the n, but I'm going to leave in a 1 minus q to the n minus 1 here, just because I've got one of those in the numerator as well that I will cancel. And then this product k goes from n plus 1 up to infinity, and then 1 minus z times q to the k. Okay, so let's bring this color coding down so we know where this came from. So I'll just put this color coding here on that sum. Okay, good. And then, well, let's do the same thing for the blue term. So here I've got my sum as n goes from 0 to infinity. Again, let's bring this color coding down. So this is from the blue terms. I start off with my stuff that doesn't change. Minus 1 to the n, z to the 2 times n, and then q to the n times 5n plus 3 all over 2. Okay, so like I said, that's the stuff that does not change. And then, well, what can I factor out in this case? Well, observe that I'm switching the order here because, well, I've got this plus sign here, so I'm going to put this term first. So here I've got a z to the I plus 1. There I have a z to the I. So I can most definitely factor out a z to the I. And then what power of q can I factor out? Well, I can factor out a q to the 2n plus 1 times I. That's got 2n plus 1 times I in that term, 2n plus 1 times I plus 1 in that term. And then I can factor out a minus I minus 1 times n. So that's actually in that second term in totality. And what will that leave me with? Well, I'll have a 1 minus z times q to the n plus 1. That's what's left over from this first term after factoring out the entire second blue term. Okay, now I'm just going to write my denominator. I'm going to write the denominator a little bit differently. So this rising product, 1 minus q to 1 minus q to the n, and then 1 minus z times q to the n plus 1. That's the first term of this product here. And then I'll pick up with the rest of the product. So this product k, now it's going to start at n plus 2 because I took out the n plus 1 term, 1 minus z times q to the k. But now, well, I think you probably see I wrote this in a way so that things are going to cancel. So let's cancel those things. So observe that this term right here will cancel this term right here, but not quite. It's not going to cancel until we notice that, first of all, when n is equal to 0, we get a 0 term. And you might say, well, it looks like I have a 0 over 0 because I have 1 minus q to the 0 over 1 minus q to the 0. But in fact, when n is equal to 0, this is an empty product. So this is equal to 1. That's kind of a technical thing that's happening here. So we can't actually cancel this yet, even though I started to cancel it, until we recognize that this sum doesn't really start at 0, it starts at 1. So let's maybe get rid of this 0 and put a 1 here. And that's because the natural 0th term is equal to 0. Now we've got this starting at 1. We'll have this top term of this rising product cancel with this thing in the numerator. Okay, good. And then, well, we have some cancellation over there in the second term as well. So notice that this 1 minus z to the times q to the n plus 1 will get canceled, well, with its companion in the numerator. Then next up, what we're going to do is a round of re-indexing on this first term. So what I'll do is I'll take all of the n's and I'll replace them with n plus 1s. But what is that going to do for me? Well, that means that this sum will now start at n equals 0. So now I've got this sum as n equals 0 going to infinity. We have a minus 1 to the n plus 1 now. We have a z to the 2n plus 2. And then we have a q to the n plus 1 times 5n plus 8. And then a q to the minus I times n plus 1. And then, well, that's the entire numerator now after that simplification. And now we've got 1 minus q all the way up to 1 minus q to the n. After reindexing, it changes that ending point from q to the n minus 1 to q to the n. And then we'll have this product as k goes from n plus 2 to infinity of 1 minus z times q to the k. Okay, so that's looking good. And then, well, we can just bring this second term down. And since it's blue color-coded, I'll just bring it down as this blue box. Okay, great. But now let's observe that those denominators match. And since, well, those denominators match, we can simply add the numerators. Observe that what we can do here is take this minus 1 to the n plus 1, change it back to a minus 1 to the n by factoring a minus sign out. And then, well, now we've got this numerator of the second term minus the numerator of the first term. And, well, I'm going to factor out as much as I can from both of those, and we'll see what we have. So in fact, we can factor out a z to the I times a q to the I from the whole thing. So let's see where that's coming from. Here we have a z to the I and also a q to the I. That's from this q to the 2n plus 1 times I. It's from the plus 1 times I. And then over here, when we factor it out, we'll just introduce a z to the minus I. Okay, so what are we left over with after we do that factorization? So we have a minus 1 to the n, and then a z to the 2n times a q to the 2n. And then we'll have a q to the n times 5n plus 3 all over 2 minus 1 minus I times n. And then this is all multiplied into 1 minus, now we're going to have z times q in parentheses to the 2 minus I. And then after that, we'll have a q to the 2n plus 1 times 1 minus I. Okay. And then, well, that's the entire numerator. And then, well, what do we have in this denominator? Well, I'm going to write this as the rising product, 1 minus q up to 1 minus q to the n. And then I'm going to write this product starting at n plus 1 again and going to infinity, and just rewrite the internals of the product a little bit as 1 minus z times q all times q to the k. And now, well, the trick here is to recognize that this is in fact a multiple, a z to the I, q to the I multiple of another term from our family. So let's see what other term from our family that is. So I'm going to write this here. We've got z to the I, q to the I. So it looks like, 1 minus I, well, is close to playing the role of I. Look, here we have an I, here we have a 1 minus I. So perhaps this should be related to f sub 1 minus I. But now there are some places where that doesn't work so much. Notice instead of here having a z to the n, we have a z to the 2n times q to the 2n, whereas like I said over here, just a z to the 2n. And then furthermore, some other things don't really seem to work out, but all of those are fixed if instead of seeing this as f sub 1 minus I evaluated at z, it's f sub 1 minus I evaluated at z times q. And then, well, let's maybe go way over here to the extreme left-hand side and way over here to the extreme right-hand side. And this is in fact the identity that we were going for. But observe that the function that we're really interested in is f sub 1 of z. So let's see what this says about that function. Okay, so we just proved the super important recursion on our f functions. Now we're going to specialize this a couple of times. So let's first specialize this to the case when I is equal to 0. So that gives us f sub 0 of z minus f sub negative 1 of z equals, well, z to the 0, q to the 0 times f sub 1 of z times q. But let's look at this f sub minus 1 of z and observe that that's going to give us a z to the 0 here and a q to the 0 here. In other words, the number 1. So this term right here is 1 minus 1 for all values of n. But 1 minus 1 is 0, so that means this numerator is always 0. But if you're adding up a bunch of zeros, you simply get 0. So that means this f sub minus 1 of z is simply equal to 0, giving us, well, this really important rule that f sub 1 of zq is equal to f sub 0 of z. Okay, and now, well, let's specialize this another time where now we'll pick the case when I is equal to 1 and see what we get out of that. So if I is equal to 1, we get f1z minus f0z equals z times q times f sub 0 of zq. But now, well, we can make some replacements. Observe by this rule right here that I'm underlining in yellow, we can take this f sub 0 of z and rewrite it. Furthermore, we can replace this f sub 0 of zq, but that's going to give us a functional equation satisfied by f sub 1 of z. So we'll have f sub 1 of z minus f sub 1 of zq, making that first replacement, equals z times q times f sub 1 of z times q squared. And then, well, I'm going to point something else out, and that is that f sub 1 of 0 is in fact equal to the number 1. So you can check that simply by plugging in z equals 0 into this thing, and observe that everything collapses down to the 0th term, which is equal to 1. So as a summary, well, we've got this family of functions f sub I. F sub 1 seems to be the most important. In fact, if we evaluate it at z equals 1, we get this product side of our identity, and it satisfies this nice difference equation. Now, where do we go from there? Now we're ready to do the last main step of our proof. So we're going to start by simplifying notation just a little bit by setting capital F of z equal to f sub 1 of z. Now, I've recalled the form of capital F of z here. And then, well, we know a couple of things. If we evaluate f at 1, we get this infinite product, which is the product side of our identities. And then also, capital F will satisfy the following recursion. So we have f of z minus f of zq equals zq times f of zq squared, and then f of 0 is 1. And this, in fact, uniquely defines f. So now what we're going to do is find another formula for f just starting with this recursion. Okay, so we'll start by expanding f of z as a power series in z. So that means the coefficients are only in terms of q. So we have the sum as n goes from 0 to infinity, a sub n of q times z to the n. Now, this is a lot simpler than our definition of f of z here, which has all of these z's all over the place, including in the denominator here, which we would expand using geometric series formula. But this original version of our function f, it was written this way, well, so that we could easily get at this product side recall we used the Jacobi triple product. Okay, so now let's really quickly observe that f of 0 is simply equal to a sub 0 of q, because all of the other terms drop off. But we know that f of 0 is also equal to 1, so that means that we know that a sub 0 of q is identically equal to 1. Okay, great. So there we've got our series expansion of f of z, just in terms of z. Okay, so now we're going to look at the other parts of this equation. So let's look at f of z times q. So that's going to be equal to the sum as n goes from 0 to infinity. We'll have a q to the n, a sub n of q times z to the n. I think that's pretty straightforward how we got there. And then, well, we've got one more thing to look at, and that's the right-hand side of our recursion. And so that has a z times q out front, so zq, and then after that it has an f of zq squared. Okay, so putting this together carefully, we'll have the sum as n goes from 0 up to infinity of, well, it's going to be q to the 2n plus 1, a sub n of q, and then z to the n plus 1. So that's what we get after moving this z times q inside. Okay, great. And now, well, now let's rewrite this equation right here in terms of our power series. So we'll start with our f of z minus f of z times q, but I'm going to put that together into one series. So what do we have? We have this. So we have the sum as n goes from 0 up to infinity of 1 minus q to the n times a sub n of q times z to the n. Okay, good. And then, well, before we write down the right-hand side, what I'd like to notice is that, in fact, the 0th term here is equal to 0. Well, why is that? Well, that's because, well, if we look over here, the 0th term is this f of 0 minus f of 0, just by taking this difference, which is 1 minus 1, which is 0. But we can also see it exactly right here. We get 1 minus q to the 0, which is obviously 1 minus 1, which is 0 as well. So since the 0th term is equal to 0, I can take the starting point and change it to a 1. That's exactly what I'll do. And then let's write down the right-hand side. But as we write down the right-hand side, we're going to re-index. So I'm going to re-index this thing by taking all of the n's and replacing them with n minus 1. So that's going to change our starting point from 0 to 1. So now I have the sum as n goes from 1 to infinity. And now this is going to be q to the 2n minus 1, a sub n minus 1 of q. And then we'll have z to the n. Okay, great. And then, well, the really nice thing about looking at it like this is that we have everything expressed in terms of z to the n. So we can simply extract the coefficients of z to the n from both sides of the equation. You know, much like we did when we proved some of our previous simpler results. So extracting those two and then solving gives us the following. So we'll have a sub n of q is equal to q to the 2n minus 1 over 1 minus q to the n times a sub n minus 1 of q. Okay, good. But now we can apply that again. We can apply that again to this a sub n minus 1. And what will that leave us with? Well, we'll have q to the 2n minus 1 times q to the 2n minus 3 all over 1 minus q to the n times 1 minus q to the n minus 1 times a sub n minus 2 of q. And of course, you can't do this forever, but you can do this until you reach a sub 0. So let's do that until we reach a sub 0. And what will that look like? Well, our numerator will be q to the 2n minus 1 times q to the 2n minus 3 dot 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 q cubed times q to the 1. Notice we've got only odd powers there. And then our denominator will be 1 minus q to the n times 1 minus q to the n minus 1 all the way down to 1 minus q. And then here we have a sub 0 of q. But let's recall that this f sub 0 equals 1 implied that a sub 0 of q equals 1. So this is in fact equal to 1. Okay. And then, well, we can do a bit of simplification here as well. So notice that we can take everything here in the numerator and, well, push them together into one term. So that'll be q to the 2n minus 1, or actually maybe I'll reverse the order. So 1 plus 3 plus dot 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 up to 2n minus 1. So in other words, the sum of the first n odd numbers. But it's well known that the sum of the first n odd numbers is equal to n squared. So that means that we in fact have q to the n squared over 1 minus q times all the way up to 1 minus q to the n times a sub 1 of n. Okay, but look at what we've got. That means we've got this nice closed form for a sub n of q. So let's write that down and then we're ready to take it home. Okay, so starting with our crazy expression for capital F of z here, and all of our previous work, most especially this equation, we came up with the following maybe nicer expansion of f of z as a power series of z. And now we're really ready to take it home. So what we'll do is evaluate this at z equals 1. So here, evaluating this f of z at z equals 1 clearly gives us f of 1. But earlier, we determined that f of 1 was this product. So we have the product as m goes from 0 up to infinity of 1 minus q to the 5m plus 1, 1 minus q to the 5m plus 4. Good. But now we'll do the same evaluation over here on the right-hand side of the equation. And that'll give us the sum as n goes from 0 up to infinity of q to the n squared over this product from 1 minus q all the way up to 1 minus q to the n. But now look at what we've got. We've got our Rogers-Ramanujan identity, or more specifically, the first Rogers-Ramanujan identity. So what we've been looking at this whole time and what we just proved is actually the first of two main Rogers-Ramanujan identities. And so, well, that leads us to really the question, what is the second of these identities? Well, and here it is. So the number of partitions of n into parts that are 2 or 3 mod 5 is equal to the number of partitions of n whose consecutive parts differ by at least 2, where the smallest part is also at least 2. And so let's observe that this has a similar flavor to the first identity. We're working mod 5 on the left-hand side, but instead of 1 and 4 mod 5, we're 2 and 3 mod 5. And then we've got the same difference condition on the right-hand side. It's just we have a different initial condition. The smallest part is at least 2 instead of the normal smallest part being at least 1. Now we can write down a version of these involving generating functions pretty easily. So I won't go through the derivation here, but we've got this product over here on the left-hand side. It's of things of the form 1 over 1 minus q to the 5m plus 2 times 1 minus q to the 5m plus 3. And then we've got this sum over here on the right-hand side. Notice that in the numerator, we've got q to the n squared plus n. That's how it differs from what we had before. Now, again, I'm not going to do a proof of this either, but the proof actually follows very, very quickly from the proof of the first identity. In fact, it's almost a little bit more natural to prove these at the same time, which is not what we did, but we could have done that if we wanted to. Okay, so there are many related identities, and maybe here's one of the famous ones. It's the Golnitz-Gordon identities, and it says that the number of partitions of n into parts that are 1, 4, or 7 mod 8 is equal to the number of partitions of n whose consecutive parts differ by at least 2, except when we have consecutive even parts, which must differ by at least 4. So as you can see, we've got these nice congruence rules over here on the left, but over there on the right, we've got something that's getting more complicated as we maybe change the congruence rules. So this really gives us this nice intuition that maybe the Rogers-Ramanujan identity is the simplest version of one of these types of identities. Now, there's another one which is called Gordon's partition theorem, and that says that the number of partitions of n that are not congruent to 0 or plus or minus I mod 2k plus 1 is equal to the number of partitions of n where the number 1 appears at most I minus 1 times, and the number of consecutive integers is k minus 1. And so this can be seen as a direct generalization of the Rogers-Ramanujan identities. I think I'll let you try to decide what you set I and k equal to produce the identities that we presented earlier. But observe that this is an infinite family of identities. And this, along with the Golnitz-Gordon identities, which were on the last slide, also have generating function versions, and you generally prove them via the generating functions, but I'll let you look up those generating functions if you're psyched. So now I guess we'll end the video with one of the Kanad-Russell conjectures, and some of these are proven. I'm not sure if this one is proven, but the story is this: like in 2010, 2011, Shashank Kanad and Matt Russell did this computer search for identities of Rogers-Ramanujan type. And so when I say Rogers-Ramanujan type, I mean that one side involves congruence mod something and the other side has this weird difference condition. Or in terms of generating functions, one side is a product and the other side is a sum. And so in their original paper, they came up with 9 of these conjectures that were verified up to, fairly large values of n via a computer. I guess fairly large values of n when you're thinking about partitions, which isn't really that big because the number of partitions grows very, very quickly. But anyway, like I said, some of these have been proven and some of them haven't. I'm not totally sure if this one's been proven or not. Maybe post in the comments if you know. This one says that the number of partitions of n into parts that are congruent to 3, 4, 5, or 6 mod 9 is equal to the number of partitions of n with smallest part at least 3 and a difference of at least 3 at a distance of 2, and that if consecutive parts differ by at most 1, then their sum is divisible by 3. So you can see that there's a lot of moving parts over there on the right-hand side. And if you look at their conjectures, the left-hand side is always this fairly nice congruence condition, but the right-hand side is always crazy like this. Okay, so I think that's where we're going to leave it for this video. If you enjoy this format, maybe post in the comments and give me ideas of other things that I could do an in-depth dive into. Obviously, I can't do videos like this super often, but I like the idea of doing a video like this every month or two, and that's a good place to stop. I thought a nice little bonus to this video would be to prove one of Ramanujan's congruence theorems. And so we mentioned a bunch of these earlier in the video, but then we mainly focused on, well, like you remember, the Rogers-Ramanujan identities. So let's recall one of these, maybe the most famous of these identities, that says for all n bigger than or equal to 0, we have the number of partitions of numbers of the form 5n plus 4 is congruent to 0 mod 5. Remember that p is our partition function, so this p of 5n plus 4 is the number of partitions of 5n plus 4. Now, we're going to use two main tools here. Both are descendants of the Jacobi triple product. So I put the Jacobi triple product identity on the board. So the first one is called Jacobi's identity. So let's look at how to derive this Jacobi's identity from the Jacobi triple product. So what we're going to do is take the Jacobi triple product, so I'll just call that JTP, and we'll make the following substitution. And that is, we'll replace all of the z's with z squared times q. Now, let's see what that immediately gives us. So over on the sum side, this left-hand side, we'll have the sum as n goes from 0 up to infinity of, that's going to be q to the n squared plus n, times z to the 2. And I think that's pretty clear how that goes over there on the left-hand side. Now, what about the right-hand side? Well, now we're going to have the product as m goes from 1 to infinity. Notice that the first portion of our product doesn't change, this 1 minus q to the 2m. But the second two, or the second and the third portions of our product will change. We'll have a 1 plus q to the 2m times z squared for this middle term. And then for the remaining term, we'll have 1 plus q to the 2m minus 2 times z to the minus 2. Okay, nice. And I think maybe an important thing to notice here is that these terms in the product contribute maybe as the first one, a 1 plus z to the minus 2. And then the second one will be a 1 plus q squared times z to the minus 2, and so on and so forth. So they contribute terms like that. The important thing here is that the first term they contribute does not have a q in it. And that is actually different from the first terms of the other parts. Those all have q's in them. So that motivates us to do the following, and that is to divide both sides of this equation by 1 plus z to the minus 2. So let's do that. So over here on the left-hand side, we're going to have 1 over z plus z to the minus 1. You'll see why we're doing this. Times the sum as n goes from minus infinity up to infinity of q to the n squared plus n, and then z to the 2n plus 1. So what we did here is we multiplied 1 plus z to the minus 2 by z over z. The z in the denominator turned that to z plus z to the minus 1, and in the numerator it just boosted this power of z up by 1. Okay, so now what we'll do is divide by that on the right-hand side as well. But let's observe, if we divide by that on the right-hand side, we will cancel out this term that I'm underlining in red. So that means that, well, what can we do? Well, we can just re-index this last third part of our product so that it starts with 2m instead of 2m minus 2. So let's just rewrite this product. So we've got this product as m goes from 1 up to infinity of 1 minus q to the 2m, and then 1 plus q to the 2m times z squared, and then 1 plus q to the 2m times z to the minus 2. So that's what this thing looks like now. And now I'm going to make the following two observations, and those are going to set up the maybe fact here that we've got this 2n plus 1 multiplier in Jacobi's identity. That means that, well, it looks like a derivative has been taken, so we're trying to motivate for how this derivative has been taken. So let's observe the following. We've got the limit as z approaches I of the sum as n goes from minus infinity up to infinity of q to the n squared plus n times z to the 2n plus 1. So that's the sum part of this left-hand side. Well, that's going to be equal to the following. So it's going to be equal to I times the sum, as n goes from minus infinity up to infinity, of q to the n squared plus n times minus 1 to the n. I just factored a z out of this, and I set that equal to I. And then I've got z to the 2n, which is like z squared to the n. But z squared, when we evaluate that at I, gives us minus 1, because I squared is minus 1. So we've got something like that. But now what I'll do is I'll rewrite that as I times the sum, as n goes from minus infinity up to infinity, of minus 1 to the n. And now this is going to be kind of tricky. It's going to be q to the quarter raised to the 2n plus 1 quantity squared. But then I've actually introduced a new q in there, so I can just factor a q out of the denominator, and well, we'll have it. So observe that if I were to multiply out this term right here using standard exponent rules, I'll get q to the n squared plus n plus 1/4. So that means actually I need a quarter down here. So now the q to the quarter down here will cancel that back up to just q to the n squared plus n. So we've got something that looks like that. And now I'll do this thing. So I'm going to take this, I'm going to write it as I over q to the 1/4. And then I'll have the sum, as n goes from 0 to infinity, of two things. So the first thing will be just what I have already, minus 1 to the n, and then q to the quarter raised to the 2n plus 1 squared. So that's just all of the non-negative parts. And then we have to encode all of the negative parts in there as well. But I can do that just by replacing n with minus 1 minus n. So this is going to be plus minus 1 to the power minus 1 minus n of q to the quarter to the power 2n plus 1 squared. Now you might say, well, why isn't that like minus 2n minus 1 squared? Well, in fact, it is minus 2n minus 1 squared after we make that substitution. But when we square it, the negative part disappears. But now let's observe, we've got the minus 1 to the n times this big q thing. And then we've got this minus 1 to the negative 1 minus n times the same q thing. But let's observe that these numbers right here are the same, except they have opposite signs. So that means they're going to add to 0. So that means this sum, when we take this limit, is in fact 0. Now I'm going to squeeze one more fact in here as well. And that is that the limit as z approaches I of z plus z to the minus 1 is equal to 0 as well. And here we can just plug I in. We get I plus I to the minus 1. But I think it's well known that I to the minus 1 is the same thing as negative I. So now what we'll want to do is take the limit of this thing that I'm boxing in orange as z approaches I, but notice that it's an indeterminate form of type 0 over 0. So the way that we'll do that is by using L'Hopital's rule. Okay, so now let's do that. Okay, so here's the identity that we ended up on the last board, and notice that this left-hand side is this quotient, and we also argued that as z approaches I, the numerator in this quotient approaches 0, and the denominator in this quotient also approaches 0. So that means we could take the limit of this left-hand side using L'Hopital's rule. So let's do that. So that's going to give us the limit as z goes to I of, so now we'll have the sum as n goes from minus infinity up to infinity of 2n plus 1 times q to the n squared plus n times z to the 2n. Again, that's by L'Hopital's rule. But then what about the denominator? Well, that's simply going to give us 1 minus z to the minus 2. But now we can pretty easily just evaluate that at z equals I, because this is no longer an indeterminate form. We do not get 0 in the denominator, well, nor in the numerator. So notice that plugging an I into the denominator is going to give us 1 minus negative 1. In other words, 2 in the denominator, which is the same thing as multiplying by a half. Now we have the sum as n goes from minus infinity to infinity of minus 1 to the n, which we gain from this z to the 2n, and then 2n plus 1, and then q to the n squared plus n. But now let's see what we get over here from doing the same sort of thing on the left-hand side. So let's observe that gives us the product as m goes from 1 to infinity of 1 minus q to the 2m doesn't change. And then we have 1 minus q to the 2m again, because z squared is going to be minus 1. That's going to change the plus to a minus. And then finally, we have another 1 minus q to the 2m for the same reason. But now we can do the following, and I'm going to leave some of this as a bit of an exercise. But now what we can do is replace q with q to the half, and that's going to turn the left-hand summand into minus 1 to the n, 2n plus 1 times q to the n squared plus n all over 2. And then we can observe that the non-negative part of this sum is equal to the negative part of this sum. So that means they'll add together to get rid of this half. And then, well, if we replace q with q to the half over here on the right-hand side, we get this product as m goes from 1 to infinity of 1 minus q to the m cubed, because observe that those three terms are the same. Okay, so, well, we've just established this Jacobi's identity. Now let's look at this next tool, which is a descendant of the Jacobi triple product identity, and that is Euler's pentagonal number theorem. Okay, so now for the proof of Euler's pentagonal number theorem, which will be the last of these two tools that we'll need to establish our theorem up there. Okay, so we're going to do a fairly similar starting step. Let's start with the Jacobi triple product identity, and we'll evaluate this where we replace q with q to the 3/2, and we replace z with minus q to the half. Now let's see what happens on the left-hand side. So we're going to have the sum as n goes from minus infinity to infinity. Let's just look at this over here. So we're going to have q to the 3/2 times n squared. So that's what's going to happen right here. And then for this term right here, we're going to have q to the n/2. But then since we've got that minus sign right there, we're going to have a minus 1 to the n out front. But now let's observe that we can pretty quickly just write that in the, well, version that we see down here. So that's going to be the sum over all integers minus 1 to the n, and then we have q to the n times 3n plus 1 all over 2. Okay, nice. But now let's see what happens to the product portion, the right-hand side, with these substitutions. So we're going to have the product as m goes from 1 to infinity of 1 minus q to the 3m. That's what we get for the first term. And then for the second term, we're going to have 1 minus q to the, let's see, that's going to be 3m minus 3/2 plus a half. So that's going to be 3m minus 1. And then notice the minus changes to a plus because of this substitution right here. And then for the last term, we're going to have 1 minus q to the 3m minus 2 for similar reasons. But now let's observe that all positive integers are either of the form 3m, 3m minus 1, or 3m minus 2. So that means we can just simply put this together all into one piece, and we'll have this product as m goes from 1 to infinity of 1 minus q to the m, which is exactly where we wanted to end up. Okay, so now that we've got everything in order, let's prove this result. So we're going to start with a fairly simple result from number theory, and this just involves binomial expansion. And that is for all primes p, x plus y to the p is congruent to x to the p plus y to the p mod p. And that's because any binomial coefficient p, choose k for instance, is a multiple of p, as long as k is not equal to p or 0. So that's why this binomial expansion would collapse just to x to the p plus y to the p when you are working mod p. Okay, nice. So now let's get into it. So we're going to start with this product as m goes from 1 to infinity of 1 minus q to the 5m times the sum as n goes from 0 to infinity of p of n times q to the n plus 1. So that's just the partition function where we've multiplied by q, and then, well, there's this infinite product right here. But now I'm going to rewrite this as follows. So I'm going to factor the q out of this, and we'll have q, and then we'll have the product as m goes from 1 to infinity of 1 minus q to the 5m over 1 minus q to the m. Because it's well known that the partition function is that infinite product that we've included in the denominator there. We proved that earlier. Okay, so now what I'd like to do is reduce this thing mod 5. So if we reduce this thing mod 5, we get that this is congruent to q, and then the product as m goes from 1 to infinity of 1 minus q to the m raised to the 5th power over 1 minus q to the m, where we use this fact up here, where x is equal to 1 and y is equal to minus q to the m. I think that's pretty clear. But now let's observe that we can simplify this a little bit by canceling this 5 in the numerator down to a 4 if we cancel that term right there. That's just a straightforward calculation. Now I'm going to rewrite this as follows. We can rewrite this as q times the product as m goes from 1 to infinity of 1 minus q to the m cubed times the product as m goes from 1 to infinity of, let's see, 1 minus q to the m. That's just splitting up that 1 minus q to the m to the 4th power into that cubed and then that to the 1st power. But now what I'll do is apply this Euler's pentagonal number theorem as well as Jacobi's identity. So that's going to give me the following expression. So I'll have q, and then I'll have the sum as m goes from 0 up to infinity of minus 1 to the m times 2m plus 1 times q to the m squared plus m over 2. So that's from Jacobi's identity right here. And then that's going to be multiplied into the product or the sum as n goes from minus infinity to infinity of, let's see, this thing right here, minus 1 to the n times q to the n times 3n plus 1 over 2. So that's using Euler's pentagonal number theorem. Okay, so let's bring that result up to the top of the board, and then I think we're pretty close to finishing it off. Okay, so on the last board, we took this thing, which was the product as m goes from 1 to infinity of 1 minus q to the 5m times the sum of our partition function, or times our partition function multiplied by q. And we worked it into the following double sum. So I've put that together into one thing. Now, here's how we want to think about this left-hand side. So let's take this sum as n goes from 0 to infinity of p of n times q to the n plus 1. And let's break it into p of 5n times q to the 5n plus 1, p of 5n plus 1 times q to the 5n plus 2, so on and so forth. So in other words, we're breaking it into its pieces mod 5, if you will. So notice the last one here will be p of 5n plus 4 times q to the 5n plus 5. Which means in this thing that expands out via this yellow bracket, the numbers that are attached to q to 5 times something are all p of 5n plus 4. They're everything that's like p of 5n plus 4. But notice that the rest of this product over here only has q to the 5th power times something, or q to the 5 times something. So that means that when we look at the entire left-hand side and we extract the coefficients of q to the 5 times something, we'll get p of 5k plus 4 for some k bigger than or equal to 0. So that tells us that perhaps we should look at the coefficient of q to the 5 times something on the right-hand side. Oh, and I made a tiny mistake here. This is not equal, this is congruent mod 5. So let's write that down. So this is congruent mod 5. That's important. And now to answer this question, we'll do a quick calculation. So let's look at 1 plus n times 3n plus 1 over 2 plus m times m plus 1 over 2. And now via a pretty simple calculation, that's equal to 1/8. And then we'll have 8 plus 4n times 3n plus 1 plus 4m times m plus 1. So really we just like multiplied and divided by 8 there. Nothing fancy went on. And now what I want to do is write this as 1/8. And then I'm going to take the stuff in parentheses and rewrite it like this. We'll have 2n squared plus 4n plus 2. And then we'll have 4m squared plus 4m plus 1. And then finally we'll have 10n squared plus 5. So that's just from expanding out what's in the parentheses and then resorting it. And now I'm going to reduce this thing mod 5. So it's pretty easy to calculate that 1 over 8, or the multiplicative inverse of 8 mod 5 is 2. So I can rewrite this as 2 times n plus 1 squared plus 2m plus 1 squared mod 5. So notice if we reduce mod 5, that 10n squared plus 5 is simply 0. So that's gone. And then I just factored the rest of that. And now I'd like to observe the following. And let's maybe fit this into a little chart over here. And that is, we'd like to calculate the perfect squares mod 5. So here I'll have x and x squared, just keeping in mind that we're working mod 5. So if we've got 0 squared, we get 0. 1 squared is 1. 2 squared is 4. 3 squared is 9, which is 4 again. And then 4 squared is 16, which is 1 again. So that means the perfect squares mod 5 are only 0, 1, and 4. But that means that this thing right here can only take on the values 0, 2, and 3. How did I get 0, 2, and 3? Well, notice that this is 2 times a perfect square. So if I do 2 times 0, that's 0. 2 times 1 is 2. And then 2 times 4 is 8. But that's 3 mod 5. So that's really 0, 2, or 3 mod 5. But then let's look at this one right here. That's just a perfect square of an odd number mod 5. But let's observe that taking perfect squares of odd numbers mod 5 will actually allow us to achieve any of those. 0, 1, or 4 mod 5. Okay, nice. And so now I'd like to observe the following, that the only way to achieve 0 mod 5 is for both of these to be 0 in the first place. Because notice if we take 2 and we add it to 0, 1, or 4, we don't get 0 mod 5. If we take 3 and add it to 0, 1, or 4, we don't get 0 mod 5. So the only way to achieve the whole thing is 0 mod 5 is for both of these to be 0 mod 5. Now, we can put that together down into this statement right here, and that is that 1 plus n times 3n plus 1 over 2 plus m times m plus 1 over 2 is congruent to 0 mod 5 if and only if 2m plus 1 is congruent to 0 mod 5. But I claim that that finishes this thing off. Because let's observe, that says that this exponent over here on the right-hand side is a multiple of 5, if and only if the coefficient is a multiple of 5. But since the left-hand side and the right-hand side are going to have the same coefficients when everything is expanded, that means that this p of 5k plus 4 is necessarily going to be a multiple of 5. But that's where we wanted to end up.